Hello. Hi everyone. Please tell me, am I audible? Is the audio, video, everything fine? Please tell me. Okay. Is the audio clear? Is the audio clear? Please tell me. Is there any echo? Volume is low? Is there any problem with the audio? If everything is fine, then we will start. Okay. So audio, video, everything is fine, right? So I can see your chat. I can see your comments in the chat. Okay. So let's start this session now. So I hope you enjoyed this All India Mock Test 1 for GATE Computer Science 2024. Please tell me, did you enjoy? The questions were very quality questions. Basically, a lot of students, they attempted this test. More than 1,000 students, they attempted this test live. So there was some load issue on the GATE Overflow website. Okay. Other than that, you just tell me the question quality. Did you enjoy the question? Did you enjoy the analysis after attempting the test? After attempting the test, when you did the analysis, did you enjoy the questions? Did you enjoy the analysis? So in this session, we are going to do a detailed discussion of All India Mock Test 1 questions. So this is solution part 2. In the part 1, Sachin Mittal sir, they have already discussed some questions, many questions they have already discussed from engineering mathematics, from operating system, algorithm, data structure, C language, compiler design. So those subjects, the questions from those subjects we have already discussed in the part 1. Okay, so this part 1 you can find on the Go Classes YouTube channel. The link I will put in the description. Now, this is your part 2. Okay, this is the part 2. So let's start now. Okay, so let me start. Let me introduce myself. My name is Deepak Punia. I have completed my MTech from IISc, Indian Institute of Science, Bangalore. And many times I have secured top rank in the GATE exam. GATE Computer Science, All India rank 53, All India rank 67, All India rank 107, 206, 256. So many times I have secured top rank in the GATE Computer Science exam. Okay, so let's start now. If you want to enroll for the Go Classes and GATE Overflow test series, the link you can find in the description, or you can just go to the GATE Overflow website. You will find this, or you can go to this website. Okay, see this website. So go to this website, go here, and you can enroll for the Go Classes and GATE Overflow test series. Okay, Go Classes plus GATE Overflow combined test series you can enroll. Okay, let's move on. One more thing. If you don't want to enroll for the complete test series, if you only want mock test, that also you can do. You can enroll only for the mock test. See this. Okay, if you only want mock test, there are total 20 mock tests in the GATE Overflow plus Go Classes combined test series. There are total 20 mock tests are there. So if you want to enroll for mock test, that also you can do. So this is your mock test package. Okay, you can enroll only for the mock test. That also you can do. The link you can find in the description. Okay, or you can just go to this website on the GATE Overflow website. Okay, you can just go to this link and you can enroll for the mock test package. Okay, so let's move on now. One more thing I want to tell you, that on the Go Classes website or on the Go Classes app, so you can download the Go Classes app from the Play Store. So this is your Go Classes app. This you can find on the Android also, you can find on the iOS also. Okay, so Go Classes Android and iOS app you can download from the Play Store or from the App Store you can download. So these two courses you can see, complete Discrete Mathematics course and complete Engineering Mathematics course. These two courses, they are completely free for all the learners. On the Go Classes website, you can go to Go Classes website, or you can go to Go Classes app. Okay, or you can go to Go Classes app. So these two courses are completely free. Remember, complete courses are free. Complete Discrete Mathematics course is free and complete Engineering Mathematics course is free. You can watch these two courses from the Go Classes website or from the app. You can watch for free. Okay, so that is enough. And just one small thing, that if you want, you can join the Go Classes Telegram group, doubt discussion Telegram group you can join. So this is the username you can see on the Telegram. Okay, on the Telegram, the link again you can find in the description. So this is the username on the Telegram. You can join Go Classes doubt discussion Telegram group also you can join. Okay, so that's enough. This was a quick promotion, nothing else. Okay, very quickly I have gone through the small points that I wanted to tell you if someone does not know. So now let's move on. And this is the last point in the promotion. If you are a GATE 2025 aspirant or GATE 2026 aspirant, GATE Computer Science 2025 or 2026 aspirant, then you can join Go Classes GATE Computer Science complete course you can join. Okay, so this Go Classes GATE Computer Science complete course, this is the complete course for GATE Computer Science. This you can join. Okay, again the link, again you can see the link you can find on the Go Classes website. Just go to the Go Classes website. Okay, and you will find the link you can find there. Okay, so just visit this website for the link. Okay, now let's solve theory of computation questions. Okay, so let's solve the theory of computation questions in this AIMT 1 All India Mock Test 1. Let's solve them. Let's start with this question. This is our All India Mock Test 1 theory of computation question. Which of the following statements is or are true for languages over some alphabet sigma? Some 4 options are given to you. Now the question is saying, if L1 and L2 are context free, then their concatenation is also context free. Option B is saying, if L1 L2 are context free, then their union is also context free. Option C, if L1 L2 are context free, then their intersection is not context free. If language L is context free, then the complement is not context free. So this is a very simple question. What will be the answer for this? Please tell me. See, context free languages, they are closed under concatenation and union, right? Okay, so you can see if you have 2 context free languages, L1, L2, they are 2 context free languages, then their concatenation will be context free. So this option A, this is correct, because what is this? This is concatenation. This is L1, L2, that is same as L1 dot L2. So this is your basically concatenation operation. Okay, so the concatenation of 2 context free languages, that will be a context free language. So option A, that is true. The question is asking for true statement. Okay, remember the question is asking for true statement. So option A will be correct. If L1, L2 are context free, then their union also will be context free, because context free languages, they are closed under union. So option B, that is also correct. What about option C? What about option C? If L1, L2 are context free, then can I say their intersection will be not context free? Tell me. If L1, L2 are context free, then can you guarantee that their intersection will be not context free? No, we cannot say that. Similarly, if L is context free, then can I say that complement of L will be not context free? Again, this I cannot say. So this is also false. Okay, remember, very simple point. These are the closure properties of context free languages. You can see context free languages, they are closed under union operation. Means if you have 2 context free languages, A, B, then their union also will be context free. Context free languages, they are closed under concatenation operation. Means if you take 2 context free languages, then their concatenation, that also will be context free. Remember, context free languages, they are closed under clean star operation, reverse operation. Okay, so you can see if you have a context free language, then the reverse of this language, that also will be context free. But you can easily see that context free languages, they are not closed. They are not closed under intersection. They are not closed under complementation, and they are not closed under difference. What that means? What this not closed means? See, this table you may have seen many times. You can see for the context free languages, these are your context free languages. You can see that intersection of context free languages For that we have written n here. What this n means? In this column, context free languages column, the operation is intersection. Then we are writing n. What that n means? This n means not closed, right? Yes or no? This n stands for not closed. This means not closed. Okay. And what this y stands for? This y stands for closed. Okay. So you can see. But what not closed means? Not closed, what that means? Please understand that, because it is very important. Okay. What this closed means? If I say closed, what that means? And if I say not closed, what that means? So assume you have two context free languages, L1, L2. Okay, L1, L2 are context free. They are context free languages. Now you tell me what this closed means. When I say they are closed, for example, when I say they are closed under union, if I say CFLs are closed under union, when I say that context free languages are closed under union operation. So what that means? When I say they are closed, then it simply means that if you have two context free languages, their union also will be context free. Means if you take the union, this union is guaranteed to be context free. Okay, this union will be guaranteed to be context free. This will be a context free language. So this is what it means. Now, what it means when I say not closed, that is interesting. When I say not closed, what that will mean? If I say not closed, for example, if I say, let me ask you a question, that L1, L2 are context free languages. What can you say about L1 intersection L2? What can you say? What can you say about L1 intersection L2? Can I say it will be a CFL? And can I say it will be not CFL? Tell me. Can I say it will be a CFL? Can I say it will not be a CFL? Which option is correct? See, very simple point. This not closed, remember this always means may or may not. Okay, this not closed. This means if L1, L2 are context free languages, and when I say CFLs are not closed, please understand this. This is very important. When I say that context free languages are not closed under intersection, then what that means? What this will mean? When I say they are not closed under intersection, this not closed, what that means? Remember, this means, please understand, this means that L1 intersection L2 that may or may not be context free. L1 intersection L2 may or may not be context free. May or may not be context free. Please understand. Okay, remember, when I say not closed, if I say that context free languages are not closed under intersection, then remember it means that L1 intersection L2 may or may not be CFL. They may be CFL, they may not be CFL. Let me give you two examples. Okay, for example, consider if I give you L1 equal to 5, is this CFL? Just tell me, is this CFL? Yes, this is CFL, very good. Okay, if I give you another language that is sigma star, is this CFL? Yes, of course, this is CFL. Now you tell me, what about their intersection? Is that CFL? L1 intersection L2, 5 intersection sigma star, that will be 5. And yes, that is CFL. Okay, yes or no? So you can see intersection of CFLs that may be CFL, right? Yes or no? Here you can see in this example, L1 is CFL, L2 is CFL, their intersection is also CFL. Now consider this example. I am giving you this language A power M, B power M, C power N. Okay, this language where M comma N, they are greater than equal to 0. Okay, so this language I am giving to you A power M, B power M, C power N. I am giving to you L2, that is A power M, B power N, C power N. Okay, now what will be their intersection? Remember, M comma N, they are greater than equal to 0. Okay, M comma N, they are greater than equal to 0 in both of them. So you tell me, what will be their intersection? What will be their intersection? Please understand, this L1 is also CFL, this L1 is also CFL, and this L2 is also CFL. L1 is also CFL, L2 is also CFL. But what about their intersection? Their intersection will be A power N, B power N, C power N. Here you can see this intersection, this is not CFL. This intersection A power N, B power N, C power N, this is standard non-CFL. So you can see these are the two examples. So here you can notice context-free language, intersection context-free language, the result is context-free language. Here you can notice CFL intersection CFL, the result is not CFL. So please understand, when I say not closed, what that means. Context-free languages are not closed under intersection operation. It means L1 intersection L2 may or may not be CFL. Is this clear? It may or may not be CFL. Okay, very simple. Now, you tell me about this question now. Now tell me, what about this question? Tell me, L1, L2, they are context-free languages. Two context-free languages you have. What can you say about L1 intersection L2? Can I say that will be CFL? Can I say intersection will be CFL? Can I say intersection will be CFL? No, I cannot say. I cannot say. Can I say intersection will be not CFL? Can I say intersection will be not CFL? L1, L2, they are context-free languages. Can I say their intersection will be not context-free? Can I say their intersection will be not context-free? This also I cannot say. Okay, so please understand, the correct answer will be this is also not there, this is also not there. The answer will be may or may not be CFL. May not be CFL. Okay, the correct answer will be the result may or may not be CFL. This will be the correct answer. Is this clear? Please tell me. Let me know. So this is a simple question. So you can solve it very easily. Similarly, you can say for L complement. Okay. So you tell me, if L is a CFL, then what you can say about L complement? What you can say about L complement? Let me know. If this language L, this is a CFL language. L is a CFL language. Now what you can say about its complement? Tell me. Can I say the complement will be CFL? I cannot say. Can I say the CFL complement will be not CFL? This also I cannot say. Okay. For example, you can easily see, consider this language L equal to 5. This is a CFL language. What will be its complement? Tell me, what will be the complement of this language? This language is CFL. What will be the complement? The complement is sigma star. That is also CFL, right? Yes or no? That language is also CFL. Very simple. So this easily you can see. Also consider this example. If I give you this language like A power, maybe what I can do, I can give you this language WW complement. Okay, this language, standard language WW complement of this language, right? This will be CFL. This is a standard CFL, but its complement means WW. This language, this will not be CFL. Okay, yes or no? So very simple, you can notice here CFL complement is CFL. In this example, CFL complement is CFL. In this example, CFL complement is not CFL. Okay, you can see this is CFL. Its complement is not CFL. So finally, what will be the answer? If L is CFL, what you can say about L complement? Can I say it will be CFL? No, I cannot say. Can I say it will be not CFL? I cannot say. The correct answer will be may or may not be CFL. May or may not be CFL. Okay, this will be the correct answer. So I hope you understood what this means, not closed. Did you understand what this means, not closed? Please tell me. So very easy. This question, this is a 1 mark easy question. But many students, they can make silly mistake here. Yes or no? Did you make silly mistake here? Please tell me. Did you make any silly mistake in this question? This is a 1 mark question. Did you make any silly mistake? The question is asking for true statement. So I can say the answer will be option A, B. Okay. Option C is not true. Option D is not true. So for this question, the answer will be A, B. This is the final answer. Okay. Let's move on now. Let's solve this question. Theory of computation. Another question from the All India Mock Test 1 for GATE Computer Science 2024. So let's solve this theory of computation question. Tell me the answer. A language L is said to be cofinite if its complement is a finite set. Okay, this definition is given to you. Means this language L will be said cofinite when its complement will be a finite set. Okay. Now, which statement is true? Again, the question is asking for true statement. Which statement is true? If L is cofinite, then can I say L is regular? Statement number 1. Remember, the definition of cofinite is already given to you. What is the definition of cofinite? L is cofinite. L is cofinite if L complement is finite. Okay. if L complement is finite. Now you tell me, in this option A, it is given that L is cofinite. What is given? The given thing is that L is cofinite. This is given to you. Okay, in the option A. Because option A is asking, if L is cofinite, then L is regular. Okay, if L is cofinite, so L is cofinite. What that means? From here, what I can say? From here, I can say that L complement will be finite. So L complement is finite. Every finite language is regular. So that is regular, right? Okay, yes or no? Okay, because remember, the question is asking, if L is cofinite, then what you can say about L? Can I say L will be regular, or can I say L will be non-regular? So remember, this is the definition given in the question. L is cofinite if L complement is finite. So it is given that L is cofinite in the option A. What this means? L is cofinite. That means L complement will be finite. Every finite language is regular. So L complement is regular. Now you tell me, if L complement is regular, then what you can say about its again complement? L complement is regular. This L complement, this is a regular language. So what you can say about its double complement? That also will be regular, right? That also will be regular. And double complement is same as L. Yes or no? So I can say that you can see L is a regular. Very simple. Okay, so very simple, because complement of regular language is regular. So you can see L complement is regular. The complement of this regular language, that also will be regular. So L will be regular. So I can say this option A, this is a true statement. What about option B? Look at option B. L equal to this type of strings you have in the language L, you have TU, where T comma U, these are strings over A comma B with the same number of A's. Okay, with the same number of A's. So this is the question that is given to you, option B. Option B is saying that language L is given to you, and language L is something like this, TU, where T comma U are strings. Okay, so here you can see T comma U, they belong to sigma star, they are strings. And the question is saying that this and this, they have same number of A's. Okay, means number of A's in T, that is same as number of A's in U. Okay, they have same number of A's. And remember, T comma U, they belong to A comma B whole star. Okay, because they are strings over A comma B. T comma U, these are strings over A comma B. Now, in this question, you just tell me a very simple point. Which type of strings you have in this language? First, you understand this language. That is your task. Okay, remember, first you should understand this language L. When I say understand this language L, what it means? When I say understand language L, it means that understand which strings belong to L, which strings do not belong to L. Understand which strings belong to L and which strings do not belong to L. Okay, so please understand that. First you understand the language you understand. After understanding the language, you solve the question. Okay, don't directly solve the question. Because many students, what they will do, they will say, okay, T, U, they should have same number of A's, there is comparison. Yes or no? Number of A's here, number of A's here, they must be same, there is comparison. Okay, there is comparison, so it is not regular. Okay, this is called by hearting. Basically, you are rote learning the concepts. Okay, this is called rote learning. You are rote learning the concepts. Okay, so please understand that first you understand the language, which strings belong to this language, which strings do not belong to this language. First you understand everything. Okay, yes or no? Which strings will belong to the language, which strings will not belong to the language. So first you at least understand the language, then you solve the question. Okay, don't do like this. If you do like this, that number of A here equal to number of A here, there is a comparison. So this is not regular. So this is not a correct way. Okay, so let me tell you. You can see here which type of strings will belong to. For example, let me ask you. Okay, some strings I am giving to you. BAA, BAA, BA, or maybe BA. Yeah, tell me. Or just let me give you this. Yes. Yeah, now tell me. This string W, look at this string W and tell me, will this string belong to L or not? I have given to you, this string W I have given to you, this string W I have given to you, will this string belong to L or not? Please tell me. This string, does it satisfy the property that is given here? This string, does it satisfy everything that is given here? Yes, it will belong to L. Why? Yes, it will belong to L. Why? Because see, it is not given what is the length of t comma u. Is it given? The length of t comma u, is it given in the question? Please tell me. Is it given how much is t, how much is u? Let me know. Let me know. In this string, what will be t, what will be u, is that given to you? What is the length of t, what is the length of u, is that given to you? No, this is not given. Yes or no? So you can see what you can do here. Very simple. This will belong to L. This string will belong to L. What you can do? You can consider this as t. Okay, you can consider this as t, and you can consider this as u. Yes or no? What you can do? You can consider this as t, you can consider this as u. So every condition is satisfied. T is a string, u is a string. So this condition is satisfied. Number of a in t equal to number of a in u. That condition is also satisfied. So you can see this string belongs to L. Yes or no? Is this clear? What about this string? One more string I am giving to you. Now you tell me about this string A B A. What about this string? Let me know. Or maybe A B A A. Yeah. What about this string? Please tell me. Will this string belong to L or not? This string, will it belong to L or not? This string does not belong to L. Why? Because whatever you do, whatever t comma u take, for example, if I take this t, this u, then also condition is not satisfied. If I take this t, this u, then also condition not satisfied. If I take this t, this u, condition is not satisfied. Whatever I do, condition will not be satisfied. Yes or no? Is this clear? So this string will not belong to L, because whatever you do, you cannot write it. Remember, this is the point. You cannot write this string. We cannot write this string. We cannot write as tu, where number of a in t is equal to number of a in u. Is this clear? This string we cannot write like that. So this string does not belong to L. Whatever you do, for example, you can consider t as empty, and you can consider this as u. Then also condition is not satisfied, because number of a in t should be equal to number of a in u. So you can see this string we cannot write. We cannot write this string as tu, where number of a in t equal to number of a in u. Okay. So finally, what is this language? Which strings will belong to this language? Can anyone tell me? See, very simple analysis. In this language L, you have this type of strings. Please understand, you have this type of strings where which is tu. Okay, which is tu. Now, number of a here must be same as number of a here. So what you can say about total number of a? You just tell me what you can say about total number of a. Remember, number of a here, that should be equal to number of a here, right? Yes or no? Number of a in both of them should be equal, should be same. What you can say about total number of a? Let's assume here number of a, that is m. Here number of a also must be m. So what you can say about total number of a? So the total number of a must be even. So I can say number of a, total number of a in the string w, that must be even. Yes or no? So very simple. This language, if you notice, this will contain all the strings which have even number of a's. One more thing, if w contains even number of a, can you write that w as tu? If w contains even number of a, can you guarantee if w contains even number of a's, then can we write it as tu? Please tell me, can we definitely write it as tu? Please tell me, definitely write w as tu, where number of a in t is equal to number of a in u. Let me know. Let me know. Can you guarantee? Please tell me. Yes or no? So please tell me. Can you write that string as tu? If w contains even number of a's, then can we definitely write that as tu, where number of a in t equal to number of a in u? Yes, that will be correct. Okay, that will be true. The answer here that will be yes. Okay, the answer that will be yes. Why? Because if you have even number of A's, like if I give you this string, consider this, I am giving you even number of A's. Okay, so let's consider this string. I am giving you even number of A's. Then what will be T? What will be U? In this string, what will be T? What will be U? Please tell me. In this string, what is going to be T? What is going to be U? So you can notice in this string there are total how many A's? Total 6 A's are there, right? There are total 6 A's. So remember, you can take, what you can do, you can take this as T. Okay, or maybe you can take this as T. Okay, what you can do, you can take this as T and you can take this as U. So you can see this string will belong to L. Okay, this string will belong to L. So I hope you understood. So this, remember this option B, that is regular, right? Yes or no? Because option B, that is nothing but strings containing A. That is strings containing even number of A's. Containing even number of A's. Okay, so strings containing even number of A's, and this language, strings containing even number of A's, this language is regular, right? Can you create the DFA for this language? Strings containing even number of A's. This is your option B. Your option B is set of strings, set of all strings that contain even number of A's. This is your regular language. You can also create the DFA if you want. Okay, let's create the DFA. The DFA will be like this. You want even number of A's. So initially, if no A is there, that means you have even number of A's, right? So initially if B is coming, then you have even number of A's. If A comes, then you will have odd number of A's. Okay, if another A comes, you will have even number of A's. In this state, when odd number of A's are there, in this state, if B comes, then you will have odd number of A's. So this is the DFA. And because you have a DFA, so this language is regular. Okay, so quite easily you can do. Now, what about the next option? Please tell me. So you can see this statement is true. First statement is true. And the second statement is also true. What about the third statement? L equal to L1 union L2, where intersection of L1 L2 is phi. If L1 is regular and L2 is not regular, then L is not regular. What about this statement? This is a beautiful question. This option C, this is very interesting. Let's see the option C. What this option C is saying? This is saying that L equal to L1 union L2. Okay, L equal to L1 union L2. And what is given? It is also given that their intersection is phi. Okay, it is also given that their intersection is phi. L1 intersection L2, that is empty. There is nothing common. Okay, now the question is saying if L1 is regular, L2 is not regular, then what you can say? If L1 regular and L2 not regular, now what you can say about L? What you can say about L? Can I say L will be not regular? Can I guarantee L will be not regular? Please tell me. Can I guarantee L will be not regular? Let me know. So here can we say L will be not regular? Okay. The answer is yes, L will be not regular. Yes, L will be not regular. If it is regular, then there is a problem. If it is regular, then there will be problem. See, just assume if, okay, assume L is regular. Then what will happen? Just assume. This is a beautiful question. Assume L regular. Just assume that L is regular. Okay. For a moment, assume L is regular. Now, you can see that L1 intersection L2 is phi. There is nothing common, right? Yes or no? L1 intersection L2 is phi. So what will be the Venn diagram? Tell me, what will be the Venn diagram? This will be L1, this will be L2. Can I say this will be L1, this will be L2? Because there is nothing common. L1 intersection L2, that is phi. There is nothing common. Now you tell me what will be L2. Here remember, this is already given, this is not regular. And this is already given that this is regular. Okay, tell me what will be L2. Can you write L2 from L comma as a function of L comma L1? Please tell me, can you write L2 in terms of L2 in terms of L comma L1? What expression you write? Please tell me. In terms of L comma L1. Let me know. Because L is union, right? What is L? L is union of these two. L is L1 union L2. Okay, now let me know. So what will be L2? Can I say L2 will be L minus L1? Yes or no? Please tell me. Can I say L2 will be L minus L1? Yes or no? Because there is nothing common. Array, there is nothing common. L1, L2, they have nothing common. So can I say, remember, L is L1 union L2. This is given to you. And their intersection, L1 intersection L2, that is 5. There is nothing common. Their union is L. Their union is L. So can I say, from L, if I remove L1, will I get L2? Will I get L2? Please tell me. Will I get L2? Yes. Okay. Now notice, if you assume L is regular, then what problem will happen? What problem will happen? If you assume L is regular, then what problem will happen? You know that L2 is L minus L1. Okay. If you assume L is regular, if you assume this is regular, this is already regular. What is regular minus regular? What is regular minus regular? Regular minus regular. Regular minus regular. That also will be regular. That is a contradiction or not? That is a contradiction or not? This is contradiction because L2 is already non-regular. So this is a contradiction. So you can write here, this is a contradiction, right? Correct. Okay. So there is a contradiction here. Did you find this question beautiful or not? See, this is a beautiful question. Okay. Yes or no? Very easily you can solve this question. This question is not hard. Again, I'm telling you. Okay. Please understand. Again, I'm telling you. Look at option C. This option C. Look at this option C. L equal to L1 union L2. This is given to you. This is the first thing. L equal to L1 union L2. Where L1 intersection L2 is 5. This condition is given to you. This condition is given to you. Now, if L1 is regular, that is given to you. L2 is not regular, that is given to you. What you can say about L? What you can say about L? Now, if you assume L is regular, there is a problem. What will happen? If you assume L is regular, see, there is something beautiful here. What is that? Because of this condition, okay, because of these two conditions, you can write L2. This condition and this condition. Okay, you can see. Because this is L1 and this is a L2. And they are disjoint. They are disjoint. They have nothing common. So from these two, you can see that L2 equal to L minus L1. Yes or no? Now, you can see if I assume, if L regular, if I assume L regular, then L2 will be regular. Then L2 will be regular and there is a contradiction. Yes or no? If I assume L is regular, then L2 will be regular. And this is contradiction. And this is contradiction. Correct. Do you agree with me? This is contradiction. Because L2 is already non-regular. It is already given to you that L2 is non-regular. So if you assume L is regular, then L2 will be regular. And that is a contradiction. So L will be not regular. Yes or no? So I can say this L. Okay, so L cannot be regular. L cannot be regular. Okay, so you can see L is non-regular. Okay, is this clear? So very simple. So this is your answer. Is this understood? Anyone has any doubt in this? Now let me tell you one thing. What students did. Let me tell you what is the common mistake in this question. Common mistake. I will tell you, I know your thought process. That is the reason this question I gave you. In this mock test, I gave you this question. Why I gave you this question? Because I know the thought process of majority of the students, what they will do, how they are thinking. Okay, see, you are not using the complete information. The common mistake is not using complete information. Not using complete information in the question. Complete info given in question. Given in the question. Is this clear? This is the mistake. The mistake is that you are not using the complete information that is given in the question. In the question, The question is saying that L equal to L1 union L2. Okay, and you can see there L1 that is given to you regular, L2 that is given to you non-regular. Okay, now if this information you have, then with this information, remember one thing, with this information, can you say anything about L? If you have this information only, if you have this information only, from this information, remember, from this information, L may or may not be regular. L may or may not be regular. Please understand. From this information, if I only have this information, then L may or may not be regular. But I also have this information that L1 intersection L2 is 5. I also have this information. This additional information I have. And from this information, what I can say? From this information, I can say that now L will be non-regular. Now L will be non-regular. Is this clear? Please tell me. Let me know. So remember, if you have this information, only this information you have, that L equal to L1 union L2. L1 is regular, L2 non-regular. With this information, I can say that L may or may not be regular. Why? For example, you can easily see. Can you give me example? For example, if I take L1 equal to 5, okay, and if I take L2 equal to A power n, B power n, in this situation, what will be L? In this situation, L will be what? In this situation, L will be non-regular. Yes or no? In this situation, you can see L1 is regular, L2 is non-regular. The union also will be non-regular. But if I give you this situation, for example, consider if I give you L1 equal to sigma star, and if I give you L1 equal to sigma star and L2 equal to A power n, B power n, now you can notice that L will be regular. Okay, so this is what I'm telling you. So please understand that if you have this information, then L may or may not be regular. But if I have this additional information that L1 intersection L2 is 5, then I can say L will be non-regular. Okay, so finally I can say for this question the answer will be what? So this statement true, this statement true, this statement is also true. What about option D? Let me know. What about option D? Sigma equal to AB. Sigma, that is AB. L equal to A power n, B A power n, W A power n. Okay, so what you can say? The question is saying L is not regular but context free. Is this true? Is this true? Let's see option D. What option D is saying? Option D is saying that you have these strings. L, your language L, that is like this. A power n, W A power n, where n is greater than equal to 1. And W belongs to sigma star. W belongs to A comma B star. Okay, this is the question that is given to you. Now, what you can say about L? Can I say L is not regular? Let me know. Can I say L is not regular? So you can see this is your language A power n, W A power n, where n is greater than equal to 1. W belongs to A comma B whole star. Now here some students, what they will think? Some students will think there is A power n, there is A power n, there is comparison. Yes or no? There is A power n, there is comparison. Unlimited comparison, there is unlimited comparison. So because there is a comparison, so L is not regular. So L is not regular. And let me tell you, this is nonsense. Okay, this thing is nonsense. If you are thinking like this is wrong. First you understand the language. I always tell you what I tell you. First understand the language. Okay, before finding is this regular or not, first you understand language. So what is language L? Which strings belong to L, which strings do not belong to L? First you understand. Yes or no? So you tell me, what is this language? Can anyone tell me? What is this language? See, very simple. W is any binary string. Yes or no? W is any binary string over A comma B. Now the question is saying n is greater than equal to 1. N is greater than equal to 1. Now you can easily see that all the strings which start with A and end with A, they will belong to L. In the L, I am telling you, if you start with A, if you end with A, you can do anything you want here. You can do anything you want here. This string will belong to L. Okay, basically just take n equal to 1. Just take n equal to 1. Okay, so all these strings will belong to L, right? So first of all these strings will belong to L. Also in this language L, only these strings will belong. Okay, so this is the point. Is this clear? I'm telling you that whatever string I give you, for example, let me give you this string. Okay, just tell me this string belongs to L or not. A power 3, B, A power 2. This string will belong to L or not? Just tell me. This string, does it belong to L or not? Does it belong to L? Let me know. Look at this string and tell me, does it belong to L? What about this string? A power 3, B, A power 2. Will it belong to L? A power n, W, A power n is greater than equal to 1, where W is a binary string. You tell me this string will belong to L or not? This string, yes, it will belong to L. Because if you are doing like this is W. Who told you to take this as W? Yes or no? See, if you are taking this as W and you are saying that this string does not belong to L, who told you to take this as W? Who told you? What you can do here? Here you can do like this. You can take n equal to 1. In this language, you can take n equal to 1. Because n is greater than equal to 1. So you can take n equal to 1. So basically this string you can write like this. This string, the same string, I can write like this. Yes or no? A, B, A. So very simple. So basically this will become your W. This is A power n, W A power n. So this string will belong to L. Yes or no? Is this clear? So first you understand the language. Without understanding the language, don't solve the question. Okay, did you understand this final language? What is the language here? So here you can notice the language is basically the regular expression is starting with A, ending with A, and here you can put anything. Here you can put anything, A plus B whole star. Okay, so this is the regular expression. For this language, this is the regular expression. So because you have a regular expression, because regular expression exists for L, so L is regular. So L is regular. Is this clear? Let me know. So this is another beautiful question. I hope you understood. Okay, so please don't do this that, okay, there is comparison here. A power n, we have to compare. There will be comparison, and because of this comparison, it will be, this L will be not regular. So please don't do this. This whole thing is a nonsense. This is a nonsense. Okay, so please understand the language first. This language is given to you. First you understand which strings belong to L, which strings do not belong to L. So you can see in this language L, you have all these strings which start with A and which end with A, and in between you can put anything. So all these strings will belong to L. So you can see, for example, this string, this will belong to L. This string is going to belong to L. Okay, the reason is very simple. Just take n equal to 1, because n is greater than equal to 1. So just take n equal to 1. So you can write it. This same string you can write A power 1, and this you can take as W A power 1. So you can see this string will belong to the language L. So very simple. Now finally, what is the answer? So this language, option D, this language is actually regular, right? Okay, you can see in the option D, this language is actually regular. And because this language is regular, so I can say this option D is false. The question is asking true statement, so ABC will be the correct answer. Okay, let's move on. Understood? Did you make any silly mistake in this question? So some good questions are there. This is a 2-mark question. You can get 2 marks in this question, and these are some beautiful questions are there. Okay, so just take care. Before solving the question, understand the language. Once you understand the language, then you can decide whether it is regular or not. First, you at least understand the language. Which strings belong to the language, which strings do not belong to the language. Clearly understand. Okay, after that you can decide whether your language is regular or not. Let's solve this question. So here you can see L is a language generated by this grammar. A grammar is given to you. These are the non-terminals. These are the terminals ABC. The productions are given to you. A lot of productions are given to you. How many strings of length 4 does L contain? Okay, means how many strings of length 4 this grammar can generate. You look at this grammar and tell me, is this your right linear grammar? Look at this grammar and tell me, is this a right linear grammar? See, this grammar that is given to you, let me write it. S generates, S you can replace with lambda, or you can replace with AX or BY or CZ. Okay. Now, ultimately remember, A goes to A, B goes to B, C goes to C. Okay. Remember, A generates A, B generates B, C generates C. So you can replace A with small a, because A will generate A, B will generate B, C will generate C. So you can write like this. Okay, it does not matter, because you can easily see. Once you go to A, it will generate only A. This is the only production that is given to you. So once you go here, then you will go here. Okay, so you can see A can generate A. Similarly, B can generate B, and C can generate only C. So you can write like this. This is your S. What is X? What X can generate? X can generate either lambda or BY, or I can say BY or CZ. And similarly, Y is given to you. Y is given to you, that is Y is lambda or AX or CZ. And similarly, Z is given to you, that is lambda, AX or BY. Okay. So this is what is given to you. You just tell me, is this grammar right linear or not? This grammar is given to you. Is this right linear? Look at this grammar and tell me. See, after doing these changes, you can make these changes. Okay, you can make, because A is going to A. Similarly, B can only generate B, nothing else. Similarly, C can only generate C, nothing else. Okay, so what you can do? You can replace C with C. You can replace B with small b. You can replace A with small a. Finally, this grammar you will get. You just tell me, is this grammar right linear or not? Look at this grammar and tell me. Yes, this grammar is a right linear, right? This grammar, if you notice, this is a right linear grammar. This is a regular grammar, which is a right linear. Okay, so this is a right linear grammar. Now, because it is a right linear grammar, so you can create NFA from this. From this, you can create NFA. Correct? Yes or no? From this, you can create NFA. You can create NFA from this. This grammar is given to you. From this grammar, you can create NFA. How will you create NFA? Very simple. S goes to lambda. So your starting state, that will be S. S will be the starting state, and that will be final because of this lambda. Because of this lambda, you can see the starting state will be final. This will be your starting state. S will be the starting state, and this will be final. S will be final because S can go to epsilon. Now you can see S on A goes to X. S on A, it goes to X. S on B, it goes to Y. S on C, it goes to Z. Okay. Now you can see, look at X. Please look at X. X can go to epsilon. So X also will be final. You can see X on B goes to Y. X on B, it goes to Y. Okay. So here I can say X on B goes to Y. X on C goes to Z. Next, look at Y. Y also, Y can go to epsilon. So Y will be final. You can see Y on A goes to X. Y on C goes to Z. What about Z finally? Z can go to epsilon. So Z also will be final state. You can see. So Z on A, it will go to X. Z on A, it will go to X. And Z on B, it will go to Y. This is the NFA you will get. Okay. Now, in this NFA, one thing you can notice. See, either you can solve this question from this NFA, or you can solve this question from this grammar also. Because what you can see, this is the NFA you can get, right? This is the NFA. Now, one thing you can notice. If I want to create 4-length string, then what I can do? My purpose is to create 4-length string, right? 4-length string I want to create. So this is the string I want to create. So tell me, the initial symbol, it can go, it has how many possibilities? Tell me how many possibilities you have. Because this is the NFA you have. Remember, this is the NFA you have. Okay, please tell me, once you get out of the start symbol, can you again go back to the start state? Please tell me, from the start state, once you get out, once you go here, once you go to X or Y or Z, once you go here, then can you go back to start state? You cannot. Yes or no? You cannot go. Like you can see in this grammar. In this grammar, you can notice if I go to x, y, z, if I take any of them from the start variable, if I take any of these productions, then you cannot go to start variable again. Yes or no? You cannot go back to start variable. So these, I want 4 length string. Now you tell me, for the first symbol, how many choices will be there? For the first symbol, how many choices will be there? For the first symbol, either A you can put, or B you can put, or C you can put, right? Okay, look at this NFA. From the initial state, either you can go on A to X, or you can go on B to Y, or you can go on C to Z. So for the first symbol, anything you can put. Okay, now after that you tell me, here how many possibilities are there? First symbol can be A, B, or C. You can put A, B, or C. For example, okay, from this S, you can take A and you can go to X. You can take A and you can go to X. So the first symbol can be A. Now what about second symbol? How many possibilities are there for the second symbol? Tell me. For the second symbol, only 2 possibilities are there. Okay, only 2 possibilities, because you can see from the X, from this state, either you can take this transition or you can take this transition, right? Okay, look at this grammar. Look at this grammar. In this grammar, you can easily see from this X, either you can take B or you can generate C. Correct? Then you will go to Y or Z. From this X, you can generate B or you can generate C. Then you will go to Y or Z, you will go. So you can see for the second position, okay, for the second position, either you can take B or you can take C. If you take C, you will go to Z. If you take C, okay, so remember here you have 2 choices. For the first position, there were 3 choices. Either you could have taken A, or you could have taken B, or you could have taken C. For the second position, there were 2 choices. What were those? Either you could have taken B or you could have taken C. Okay. Now if I take C, from Z, how many choices are there? Once I go to Z, how many choices I have? I only have 2 choices. Either I can generate A or I can generate B. A or B I can generate. Then I will go to X or Y. Okay, so from this Z, you can easily see, from this state Z, there are 2 choices. Okay, what are the 2 choices? Either you can take B or you can take A. Only 2 choices are there. So very simple. Now here, how many choices? There are 2 choices. Either you can take B or A. Let me take A. Actually here there were 2 choices. What are those? The 2 choices, they are B or A. These are the 2 choices. Now if I take A, then I will go to X. If I take A, I will go to X. Now from X, again I have 2 choices. Okay, from this X, again I have 2 choices. So here I can take either B or C. Okay, here I can take either B or I can take C. Either B or C. So whatever I want, I can take. Okay, for example, I can take B. So like this you can do. Okay, yes or no? And finally, this is your final state. So you can take B and you will go to Y, and Y is your final state. Is this clear? So did you understand? See, this language, this grammar is given to you. This is the given grammar. Okay, from this grammar, you can easily find out these simple observations you can make. From here, if you make one 4 length string, then one thing you will observe that here you can put anything, but there are, okay, so there will be 3 choices here. There will be 2 choices here, 2 choices here, 2 choices here. Yes or no? There will be these many choices. After that, there will be these many choices. Do you agree with me? Please tell me. This analysis, did you understand? This analysis, did you understand? Please tell me. So you can see, this is a grammar. This is a beautiful grammar. Okay, a very simple, beautiful grammar. This is the right linear grammar is given to you. You can see, this grammar is given to you. This is a right linear grammar. Because this is the right linear grammar, so you can create NFA. If you want, you can create NFA. Okay, now you can easily notice that for the first symbol, if you are creating a string, if I create some string, if some string I create, if I generate some string I generate, then for the first symbol, there are 3 choices. I can take A, or I can take B, or I can take C. But after that, you can notice I only have 2 symbols. Okay, if I am here, if I am standing here in this state X, then I have 2 choices only, either B or C, only 2 choices. Similarly, if I am standing here in state Z, then I have two choices only, either B or either A. Similarly for Y, if I'm standing here, then two choices are there, either A or C. Okay, so this is what I'm telling you. Okay, so finally your answer you can see that will be how many four length strings you can create. Let me know. So if I want to create how many four length strings I want to create, so very simple. Here there are three choices. Here there are three choices. There will be two choices. There will be two choices, and there will be two choices. So how many strings I can create? That will be, the answer will be 3 into 2 power 3. That will be 24. These many strings you can create. Is this clear? Let me know. Okay, so this is quite simple. Can you do a general solution? For this grammar, can you give a general solution? This grammar is given to you. This grammar, how many n length strings it will generate? Okay, let's see the general solution. Let's see the general solution. How many n length strings? How many n length strings I can generate? I want to generate n length strings. How many n length strings? G generates. G generates. So tell me, how many n length strings this G will generate? So if I want n length string, okay, this is what I want, right? So you can see for the first position, there are three choices. There are three choices for the first position. You can put A or B or C. Okay, you can put A or B or C. But after that, you will have only two choices. There will be two choices here. After that, there will be two choices here. Okay, after that, there will be two choices. Okay, after that, everywhere you will have two choices. So your answer will be what? That will be 3 into 2 power n minus 1. Yes or no? Correct? So this will be your answer. Okay, 3 into 2 power n minus 1. So very easily you can solve this question. I hope you understood. Okay, you can also write the recurrence relation if you want. Okay, basically, if you want, they can also ask you recurrence relation in this question. The recurrence relation for Sn. What is Sn? What is Sn? Sn is number of strings generated, number of n length strings, number of n length strings generated by G. Okay, number of n length strings generated by G. So what will be the recurrence relation? Tell me. Sn, this is the number of n length strings. How many n length strings you can generate? Number of n length strings. Okay, so how many n length strings I can generate from G? This is your Sn. So you can see Sn, you can easily see. If I want to generate a string, then what I will do? If I want to generate a string, then what I will do? Then what I will do? Okay, here, remember, here I have three choices. Here I have three choices. Okay, after that, you can see there are only two choices each, right? Yes or no? Okay, so you can easily see. Here I can put any symbol. I can put A or B or C I can put. But after that, what will happen? Only two symbols I can put. Okay, means either B or C I can put. Either B or C I can put, like that. Okay, so you can see. Okay, here I can put all the three symbols. How can I write the recurrence relation? In this place, I can put all the three symbols. After that, what I can do? After that, what I can do? Once I put some symbol here, for example, if I put A here, okay, then only two choices are there. How to write the recurrence relation? Maybe you can think about it. How to write the recurrence relation means number of n length strings. How many n length strings will be there? So you can see for the first position, I can put any of them. I can put either A or B or C. Now, whatever I put after that, because of this A, if I put A, then I can put B comma C. Okay, so if I put A here, then I can only put B comma C, nothing else. So maybe you can try. Okay, maybe, okay, so maybe you can try this, maybe you can think about it. Okay, so what will be the recurrence relation? Either it will be, let me tell you, either it will be 3 into Sn minus 1, this Sn, either it will be 3 Sn minus 1, or it will be 2 Sn minus 1. Okay, so you can check it out. You can check it out what will be the recurrence relation here. The first symbol can be A, B, or C. You can put any symbol here. How many n length strings I can generate? This type of n length strings, how many I can generate? So you can see that the first symbol I can put A, B, or C, whatever I want, I can put it. And then I think it will be Sn equal to 3 Sn minus 1. Yes, yes. Okay. Yeah, it is simple. Okay, just let me just tell you. Okay, let me quickly tell you. So what is this? Tell me. Actually, in this G generates this type of strings. Okay, see, G generates what type of strings G will generate? See, it is very simple. G will generate this type of strings that if you are putting A here, now here you cannot put A. Yes or no? Is this clear? So if you are putting A here, then here you can only put B or C. Similarly, if I put, for example, B here, if I put B here, now here you cannot put B. You cannot put B. Here either you can put A or you can put C. Okay, so this type of strings G will generate. Yes or no? So basically, this G generates this type of strings. G generates, okay, this language G, this grammar G, this will generate this type of strings. Strings with no conjugative two same symbols. Strings with no consecutively same symbols. Yes or no? No consecutively same symbols. Consecutively same symbol. Okay, so this type of strings are there. Yes or no? Did you understand? Please tell me. Did you understand? So remember, you can easily see this is the observation we have already made, that if the first symbol is A, then the next symbol will be either B or C. So you can see if this symbol is B, then the next symbol will either be A or C. Okay, yes or no? Similarly, you can easily notice if this symbol, for example, if this symbol is A, then here you cannot put A. Okay, then you can see either it will be B or it will be C. So I can say what is Sn? Sn is strings with no consecutive same symbol. Okay, no consecutively same symbols. So in this situation, how to write the recurrence relation for these strings? Strings with no consecutive same symbol. So what is Sn? What will be Sn? Sn will be number of n length strings with no consecutive same symbols. Number of n length strings. Number of n length strings with no consecutively same symbols. No consecutively same symbols. Okay, yes or no? Is this clear? Very simple. So remember what Sn will be. Sn will be number of n length strings. Number of n length strings with no consecutively same symbols. You cannot put any consecutively same symbols. Okay. So now you can write the recurrence relation for this. For this, now you can write the recurrence relation. If you have, these are the n choices. Okay, these are the n places. Then what we do not want any consecutive same symbol. Okay, so you just tell me here. Okay, let's assume so now, okay, so Sn is number of n length strings with no consecutively same symbols. Okay, so what I can do here, alternate. So now if I start with some symbol, like if I put A here, let me just put A here. Now here you should not have consecutively same symbols. Okay, so Again, I think. Okay, just let's assume. Okay, let me just ask one question to you. Please tell me, assume this is perfect. Assume this is perfect means assume, okay, that here you have no consecutive same symbols. Okay, so how many you can create here? Assume here you have no consecutive same symbol. How many you can create? Please tell me. No consecutive same symbol. How many you can create? Just assume this is perfect. Just assume this is perfect. Assume this is perfect. So tell me, how many you can create? Let me know. How many you can create? This will be Sn minus 1. Yes or no? Yes or no? Agree with me? Did you understand what I'm telling you? Because you know what is Sn. So what will be Sn minus 1? You already know what is Sn. So what will be Sn minus 1? Tell me. What will be Sn minus 1? Sn minus 1 will be length of n minus 1 strings. Sorry, number of n minus 1 length strings. Correct? So this is what I'm asking you. Very simple. This is your string. In this string, you just tell me. Let's assume so far here everything is perfect. Just assume. I am assuming this, that here everything is perfect means here there is no consecutive same symbol. Okay, here let's assume no consecutive same symbol. So how many I can create? Here I have no consecutive same symbol. And because I have no consecutive same symbol, so how many I can create here? So I can create Sn minus 1. Yes or no? You just tell me, after creating Sn minus 1, what about this? How many choices I have here? What about this? Please tell me. How many choices will be there? Okay, did you understand my point? I am telling you, assume this is perfect. Assume the n minus 1 symbols, these are perfect. These are the n minus 1 symbols. Assume these n minus 1 symbols, these are perfect. Okay. Now, so you can see Sn minus 1 because no consecutive same symbol. So you can see that will be Sn minus 1. Now you tell me, after this, how many choices for the last position? After doing this, means here you don't have any consecutively same symbol. Okay, so how many strings you can create here? How many strings I can create here? That will be Sn minus 1. Okay, in this area I can create Sn minus 1 strings. Okay, for the final position, how many choices will be there? Just tell me. This is a simple question I'm asking. Now you tell me, for the final position, how many choices will be there? There will be only 2 choices, right? Okay, because if this is a B, then you can either put A or C. If this is A, then you can put B or C. If this is C, you can put A or B. So for the last position, there are 2 choices. So your final answer will be, so you can just easily see. So I can say Sn will be 2 into Sn minus 1. So Sn will be 2 into Sn minus 1. Okay, so this is your final answer. I hope you understood. Did you understand? Let me know. Did you understand? So you can see how many n length strings you can create. How many n length strings you can create. So that will be Sn. That will be equal to 2 into Sn minus 1. This will be the recurrence relation. And what will be the initial conditions? Here, what will be the initial conditions? The initial conditions will be, you can see S1 will be 3. Okay, this is the initial condition. S1 will be 3. Okay, because 3 one length strings I can create. 3 one length strings can be created. Strings possible. Okay, 3 one length strings possible. So this is your answer. Please tell me, did you understand the complete analysis of this question? In this question, we have seen what is the answer, we have seen the general answer, and we have also seen what is the recurrence relation. Did you understand how to write the recurrence relation for this question? This logic, did you understand? Please tell me, did you understand this logic? I want to write recurrence relation. So I am assuming Sn, that is number of n length strings. Okay, how many n length strings are there with no consecutive same symbol? So what I can do? Very simple. Just assume that here everything is perfect. Okay, in the first n minus 1 symbols, just assume that here everything is perfect. If everything is perfect in the first n minus 1 symbols, if everything is perfect, then how many strings I can put in the first n minus 1 symbols? In the first n minus 1 symbols, how many strings I can put? I can put Sn minus 1. Okay, Sn minus 1, these many strings I can put. Finally, for the last position, there will be two choices. For the last position, there will be two choices. So your answer will be Sn equal to 2Sn minus 1. So I hope you understood this analysis. Okay. So for this question, the answer will be 3 into 2 power 3, that will be 24. But the general answer will be what? But the general answer, that will be 3 into 2 power n minus 1. This will be the general answer. And what will be the recurrence relation? The recurrence relation, that will be 2Sn minus 1, where S1 equal to 3. This will be the recurrence relation. So we have seen everything in this question. Okay. So let's move on now. Now let's solve this question. This is a push down automata question. What is the language recognized by this following push down automata? The stake alphabet of P, that is A, B, this symbol is given to you. This is called bottom symbol. Okay, this symbol, this is called bottom symbol. So you can see this stake alphabet is already given to you. That is A, B, and this bottom symbol. Where this bottom symbol, this is the stake, initial stake symbol. The alphabet of P, that is A, B, and marker. This is your AND marker. You can see this symbol, this is used to mark the end of the input. Okay, what this means? This means number of C in X. Okay, how many symbols C are there in X? Now this PDA is given to you. The question is asking what are the language recognized by this PDA. So what will be the answer for this question? What will be the language recognized by this PDA? So you can easily solve this question by taking some examples. By taking some example, you can easily solve this question. See what we are doing in the first state. Here this is the final state, right? Here this is the final state. Okay. So here you can notice in the first state what we are doing. You can see this is the bottom symbol, right? What is this symbol? This is the initial bottom of the stack symbol. Initial bottom of stack symbol. Bottom of stack symbol. Okay. So you can easily see that if A is the input on bottom of the stack, then insert A. Okay. Push A on the stack. Similarly here, if A is the input and on the top of the stack you have symbol A, then you push another A. Okay. You can see if the input is B, on top of the stack you see A, then you pop it. Then you pop this A from the top of the stack. Okay. Now you can see if this symbol comes in the input, and marker symbol, and of input, and on the top of the stack you see A, then you keep it and you go to the final state. Or if the AND marker comes, on top of the stack you have bottom symbol, then you keep it as it is and you go to final state. So this PDA is given to you. Some options are given to you. Okay, let's solve it. So which string this PDA will accept? See, the PDA is very simple. Let me tell you that this is your state number 1. Let me tell you here that this is the state number 1. In the state number 1, there are 3 transitions. What are those? The 3 transitions are like this. If symbol A comes and on the top of the stack you have this symbol, then what you do? Then you push this symbol A. Okay, push it. Now, if this symbol comes on top of the stack you have A, then you again push it. If this symbol comes, if this symbol B comes on top of the stack you have A, then you pop it. Then you pop it. Okay. And here you can see if the AND marker comes and on top of the stack you have A, then you keep it as it is and you go to state number 2. Or here you can see if AND marker comes on top of the stack you have bottom symbol, then you keep it as it is, go to state number 2. So this PDA is given to you. This is the PDA that is given to you. So which strings will be generated, or I can say which strings will be accepted by this PDA? So what you can do, take any string. Okay, let me take. For example, if the first symbol is A, you tell me what this PDA will do. Let's see what this PDA will do. I am giving you W. If the first symbol is A, what this PDA will do? Please tell me. On the top of the stack, initially you have this symbol. If A comes, then what you will do? You will push it. Yes or no? Okay, in the input, if A comes, then what you will do? You will push it. On the top of the stack, initially you have this symbol, bottom symbol. Okay, so what you will do? You will push it. If another A comes, A on A, again you will push it. Okay, so here you can notice this is basically the push move. These are the push. And this is the pop. This is the push move. This is the pop move. So you can easily see if another A comes, then again you push it. If B comes, what you will do? If B comes, what you will do? Then you will pop. If B comes on the input tape and on the top of the stack you have A, then you pop it. Then this will be gone. Okay. If another A comes, in this state 1, if another A comes, you will again push it. Right? Okay, yes or no? If B comes, what you will do? Then you will pop it. Okay, after that, if this symbol ends, okay, if this string ends, then you can easily see on top of the stack there is A. So you will go to the final state. So this string will be accepted. Yes or no? This string will be accepted. Correct? So I can say this string will be accepted. This will belong to L. So because of this, which options are gone? Please tell me. Let me know. Which options are gone? You can see this string is accepted. So here you can easily see that this string AAB, AB, this string belongs, is accepted by this, is accepted. Okay, so which option is gone? Because of this string, which option is gone? You can see the first option is gone because the first option is saying A power n, B power m. Okay, but here you can notice after B, A can come. Okay, so this first option is gone. Option B is also gone. What about option C, D? Notice this string also will be accepted. For example, AB. This string also will be accepted. Okay, this string will also be accepted. So here you can see this option is also gone and option C will be the answer. Is this clear? You can check in this PDA, you can check AB, that will be accepted. Okay, what will happen? In this PDA, notice in this PDA what will happen? If I give you this string AB and marker. Now what will happen? Let me tell you. Initially this symbol you have on the stack. If symbol A comes, then you will push it. If symbol B comes, you will pop it. If symbol A comes, what you will do? You will push it. If symbol B comes, you will pop it. At the end, you will go to state number 2. Okay, so you can see this string is also accepted. This string is also accepted. So you can easily see that for this question, the answer will be option C. Is this clear? Please tell me. Let me know. Is this clear? So very simple. This PDA was quite simple. Okay, actually in this PDA, what is happening? Let me tell you. What this PDA is doing. See, this is your state number 1. This is the initial state. Now the PDA is doing like this. That initially there is a bottom symbol. The PDA is doing like this. That if symbol A comes in the string, and if this is the stack symbol, on top of the stack you have this symbol, then just push it. Okay, then just push it. So this is what we are doing. If another A comes, on top of the stack there is A, then what you do? Then again you push it. Okay, This is what your PDA is doing. So these are the push moves. Okay, these are the push moves. So the PDA is basically saying that if A is coming, I have no problem, just push it. Okay. Now you can see if B comes, on top of the stack you have A, then you pop it. Okay, then you pop it. So this is your pop move. Okay, yes or no? Now if another B comes on top of the stack you have A, then again you pop it. Now let's assume A comes. Okay, in the input A comes and this is your stack. Remember, this is your input. On the input A comes, on the top of the stack there is A. So this move you can take. Basically, again what you will do? You will push it. Okay, again you will push it. Right? Very simple. Now you can easily notice one thing. Can you have, okay, how many B's I can have maximum? Now, how many B's I can put maximum? For example, can I put 3 B's? Now, if I put 3 B's, there is a problem. If I put 3 B's, now there is a problem. Because for this B, you will pop it. But there is no such move. Yes or no? There is no such move. Correct? Yes or no? So this B, look at this B on bottom. There is no such move. We have no such move. So here you can note this string will be rejected. Look at this. This string will be rejected. Okay, because there is no move. In the input, you have B. On top of the stack, you have this symbol. Then you can notice there is no move. So this string will be rejected. So maximum, you can put maximum 2 strings, you can put, say, maximum 2 Bs. Okay, maximum 2 Bs you can put. Okay, so you can see if 1 B is also there, that is also fine. Now this symbol comes, now it will be accepted. Now this will be accepted. Okay, so this is what is happening. You can see here, if AND marker comes, on top of the stack you have A, then just go to final state. If AND marker comes, if the bottom symbol comes, then also go to the final state. Okay, so your language, let me tell you, the language will be like this, that you have all the strings W belonging to AB star, W belonging to AB star, such that in every prefix this will happen. In every prefix, okay, whatever prefix you take, in every prefix of W, basically in this W, whatever prefix you take, if you take any prefix, in this W you can take any prefix you can take. In this prefix, what will happen? Okay, in every prefix, what will happen? Number of A's will be greater than or equal to number of B's. Okay, in every prefix this will happen. In every prefix, number of A's will be greater than or equal to number of B's. This is what will happen. Okay, very simple. So this is your language. Your language will be all the strings such that in every prefix, number of A will be greater than or equal to number of B. So this is your question. Very simple question. Okay, so for that question, for the previous question, you can see for this PDA question, the answer will be option C. This will be the answer. Okay, quite simple. Let's move on now. Now let's see this question from the TOC, and this is very interesting question. This is the most beautiful question from the TOC in this test. Is there anyone here who did this question correctly? Who got the correct answer for this question with the correct logic? Is there anyone here who has confidence that I got the correct answer, also I know the correct logic? The correct logic to solve this question I know. Is there anyone here who did it correct? This is a beautiful question, let me tell you. In future GATE exam, this type of question can come. This question I have taken from Stanford University. A very beautiful question. So let's solve it. So this question, read this question. Suppose that you have a collection of n recursive enumerable languages. There is a collection of n recursive enumerable languages L1, L2, Ln. Okay, over the same alphabet. They are over the same alphabet sigma. And there is a property. What is the property? Every string of sigma star belong to exactly one of them. Okay, whatever string you take, that will belong to exactly one of them. Okay, means, can you tell me what will be their intersection? Can you tell me what will be their intersection? See, every string of sigma star belongs to exactly one of them. Whatever string you take, for example, if I take this string, this will belong to exactly one of them. Okay, yes or no? If I take this string, this will belong to exactly one of them. So you tell me, if I take two languages L1 intersection L2, what that will be? That definitely will be phi. Okay, basically what will happen here? One thing you can observe, if you take intersection, then that will be phi, correct? If I take Li intersection Lj, that will be phi. Yes or no? Agree? Where I is not equal to j. So you can see there are n languages and all are RE languages. These are RE languages such that every string, whatever string you take, that will belong to exactly one of them. It means if you take their union, then you will get sigma star because every string is present in exactly one of them. So if you take their union, you will get sigma star, and every string of sigma star belongs to exactly one of them. Now the question is asking which is true for these RE languages. All are undecidable or are decidable. At least one of them is undecidable. You cannot determine their decidability. You cannot determine their decidability from the given information. So what will be the correct answer? What will be the correct answer? Okay, see, this question is actually very easy. You might be thinking that this is a complicated question. You are thinking, I know, many of you are thinking that this is a complicated question, but I want to tell you one thing. This is extremely easy question for 2 marks. Okay, very easy question. There is a popular theorem in theory of computation. Do you remember that theorem? Complement theorem of RE languages. Do you remember this? There is a very important theorem. Complement theorem of RE languages. Let me tell you what this theorem says. This theorem says that if, what this theorem says, let me tell you. Understand this theorem. This theorem says that if L and L complement are RE, Okay, if they are RE languages, if L and L complement, if they are recursive enumerable languages, then L will be recursive. Then L will be actually recursive. Okay, this is what this theorem says. Anyone here who does not know about this? This is a standard theorem. In our lectures, we have seen this theorem with proof. Okay, so you can see very simple theorem. So this is a very important theorem, remember, very, very, very important theorem. From this theorem, a lot of questions can be created. So this is complement theorem of RE languages, recursive enumerable languages. This theorem says that if L and L complement both are RE, if L and L complement both are RE, then they definitely will be recursive. Then they definitely will be recursive. Okay. Now understand this theorem, what this theorem is saying. This theorem is saying if L and L bar, if they are recursive enumerable, then they will definitely be recursive. So you tell me, is this possible? You tell me, like, let's assume these are the recursive languages and let's assume these are the RE languages. Is this possible that L is here, L complement is here? Is this possible? Just tell me. This diagram, is it possible? Let me know. Look at this diagram and then tell me, is this possible? Is it possible? Is it possible? Tell me. This type of situation is possible or not? Remember, R means recursive. Here R means recursive. And RE means recursive enumerable, that you already know. Recursive enumerable. Okay, so you tell me, is this possible that L, L complement, they are RE, both are RE but not REC? Is it possible? The answer is no. The answer is no. This is never possible, because what I told you that if both are RE, then they will be recursive. Please read this statement. This theorem, please read this theorem and tell me, did you understand this theorem? If L and L complement are RE, if they are recursive enumerable, then they will be recursive. Then they definitely will be recursive. Okay, means if L, L complement, if they are RE languages, then they definitely will be here. They will be recursive. Okay, so remember, is this possible? This type of situation, is it possible? The answer is no. This is not possible. Okay, means if L is recursive, L complement, if both are recursive, then they will be RE. This is possible. Okay, this is possible. Understood? Yes or no? Very simple. So now I am asking some questions. I am asking. You tell me the answer for all these questions. But understand this theorem. This is very important theorem. And this is a standard theorem. You must know this. I assume that if you have studied the theory of computation, then you already know this theorem. In our lectures, in the Go classes lectures, theory of computation lectures, we have seen this theorem with all the variations, with the proof, everything we have seen. Okay, so you can see this is the theorem that if L and L complement are both RE, okay, they are both RE languages, then they definitely will be recursive. Then L, L complement are definitely recursive. Recursive means decidable. The another word for recursive, that is decidable. Yes or no? Okay, now I'm asking some questions and you tell me what will be the answer for these questions. Consider this. Is this possibility? You just tell me, is this possibility? Like, these are the recursive enumerable languages, these are the recursive languages, and here you have not RE languages. Is this possible? This type of situation is possible or not? Please tell me. Look at this diagram and tell me, is this type of situation possible or not? Is there a possibility? Is there a possibility? Yes, there is a possibility. Here you can notice L complement both are recursive. There is possibility. For example, you can take L equal to A power n, B power n. Okay, what you can do? You can take L equal to A power n, B power n, and you can take L complement. So here you can take L complement. So you can see that L is also recursive. This is also recursive, and L complement will also be recursive, right? Yes or no? So both recursive are possible. L complement both are recursive. This is possible. Yes or no? This is possible. L complement both are recursive. This is definitely possible. Is this possible? Both are not RE. Is this possible that both are not RE? Please tell me, is this possible that both are not RE? Yes, this is also possible. Please tell me, Did you understand? Both are not RE. Means both not RE. This is also possible. Both are not recursive enumerable. Can you give me example? Can you give me example that both are not RE? Is this possible? Yes, this is possible. For example, you can take L equal to set of Turing machines where Lm is infinite. Okay, and you can take L complement, that is set of Turing machines where Lm is finite. Okay, so both you can see they are actually not RE. Okay, here you can easily see here this L comma L complement both are not RE. This is also not RE. You can apply the Rice theorem. This is also not RE, and this is also not RE. Okay, they are both not RE. This example, is this clear? You can see you can apply the Rice theorem. Set of Turing machines where you have this Turing machine, this M is a Turing machine. Okay, here you can note this M, this is a Turing machine, this M is a Turing machine. So you can easily see all the Turing machines whose language is infinite, that is not RE, and this language, all the Turing machines whose language is finite, this is also not RE. So both not RE, that is definitely possible, no problem. Okay, is this possible? Is this possible? Please tell me. This possibility means L is RE and L bar is not RE. Is this possible? Yes, this is also possible, no problem. This is also possible, right? Can you give me one example? You can take, for example, you can take this LM where? Okay, so can you take, tell me, for example, here I can say, okay, give me one language which is a RE but not REC. Which is RE but not REC. Any language. For example, I can say M accepts AB. Okay, M accepts AB. So this language, this is actually RE but not REC. Look at this language. M accepts ABC. Okay, so this language, if you notice, this is actually RE but not REC. You can apply the Rice theorem. So this is actually RE but not REC. Okay, what about this complement? This complement, M does not accept AB. M does not accept AB. This language is actually not RE. This language that is actually not RE. Okay, this language that will be not RE. Is this clear? So you can see M accepts AB. Here M is a Turing machine. Here M is a Turing machine. Here M is a Turing machine. So you can see M accepts AB. This will be RE but not REC. Oh, you can see L complement. M does not accept AB. This is actually not RE. So this is also possible. What about this one? Is this possibility that both are RE and here? Is this possibility? This is impossible, right? Because remember I told you that if L comma L complement are both RE, then what they will be? Then they will be recursive. Yes or no? Okay, if both are RE, then they will be recursive. Then will definitely be recursive. Yes or no? Will be recursive. Okay, so remember, this is not possible. Is this clear? Both RE and not REC. This is not possible. So please understand what is not possible. That L complement. Okay, they are both RE but not REC. Is this possible? Tell me. These two languages, they are RE but not REC. Is this possible? They are RE but not REC. This is never possible. Okay. Is this clear? Because you can see if they are RE, if they are inside this RE circle, L comma L complement, if they are inside this RE circle, then they must be in the REC circle. They must be inside the REC circle. For example, is this possible? Again, this is impossible. Because if L is recursive, then L complement will be recursive, right? Because you know recursive complement is recursive. So this is also not possible. Because if L is recursive, then L complement will also be recursive. Okay, so this is also not possible. What about this one? Again, this is not possible. Because again the same thing, if L recursive complement, the recursive language complement will be recursive. So again you can notice that if L is recursive, then L complement will be what? Then that also will be recursive. So this is also impossible. So did you understand all the possibilities? So what is not possible? Very simple. L comma L complement, if they are RE, then they definitely will be REC. So this is the result. I hope you understood. So remember, in other words, it is not possible to have both RE but not REC. Okay, both L and L complement, they are RE but not REC. This is impossible. Impossible. So very simple. So this is the final theorem. You can see a language is decidable if and only if both L and L complement are RE. Okay, because remember what will happen. See, you tell me, if L is decidable, then L complement also will be decidable. Yes or no? If L is decidable, then what will happen? Then L complement also will be decidable. That you already know. Okay, decidable means recursive. The another word for decidable, that is recursive. So please understand that recursive means decidable. Okay, recursive. The another word for recursive, that is decidable. Correct? Okay, so if L is decidable, then L complement will be decidable. Then can I say both are RE? L and L complement are both RE? Yes or no? Is this clear? Because of course every decidable language is RE. Okay, yes or no? You can see, if L is decidable, then L complement also will be decidable. Every decidable language is RE. So L and L complement, they will be RE. The same thing we have seen. If both are RE, then they will be decidable. So this is the circle. This is the complete circle. I hope you understood. Is this clear? So finally I can say L is decidable if and only if what? L is decidable if and only if both L comma L complement are RE. Both L and L complement are RE. So this theorem, understood this theorem? Okay, very simple. Because remember, if L is decidable, then L complement also will be decidable, because you know that recursive complement will be recursive. The complement of recursive language is recursive. So you can see that if L is decidable, then L complement will be decidable. Now you can notice every decidable language is RE. If L is decidable, then L is RE. If L complement is decidable, then L complement is RE. Every decidable language is RE. So they both will be RE. We have seen that if they are both RE, L and L complement, if they are both RE, then they will be decidable. So this is the complete circle. So I can say L is decidable if and only if both L and L complement are RE. Is this clear? So this is the result that we have seen, this theorem we have seen. Now let's come back to the question. But before that, I want to tell you, this same thing we have seen in this lecture, complement theorem of RE languages. See this. This lecture is already available on the Go Classes YouTube channel. So if you are interested in the proof, you can see here. This complement theorem of RE languages, the proof, if you want the proof, just watch this lecture. Okay, this lecture you can watch on the Go Classes YouTube channel. Is this clear? Is there anyone here who is curious about the proof? If you are not curious, then don't worry. But if you want to know the proof, very simple proof. The proof is extremely simple. Okay, so you can see the proof is very simple. You can find on the Go Classes YouTube channel. Okay, with proof. I can say you can see this theorem with proof on Go Classes YouTube channel. This lecture is already available. You can see. Okay, so let's move on now. Now let's solve this question. Okay, you just tell me one thing. In this question, if I take n equal to 2, then what will be the answer? In this question, if I take n equal to 2, just take n equal to 2. Okay, now tell me, if I take n equal to 2, what will happen? In this question, take n equal to 2, what will happen? Anyone want to tell me? In this question, if I take n equal to 2, means you have two languages. Okay, you have two RE languages, L1, L2. Okay, two RE languages you have. If you take n equal to 2, because I am taking n equal to 2. So you have two RE languages. They are RE languages. This is already given to you. They are RE languages. In the question, it is given to you that they are RE languages. Okay, so they both are RE languages. This is already given to you. You can notice that you have RE languages. Okay. So they are actually RE, recursive enumerable. So now you tell me, what will be the relation between them? If you have only two languages, then what will be the relationship between them? The question is already saying their union. The question is saying their union is sigma star. Their union is sigma star and their intersection is phi. Their union is sigma star, their intersection is phi. So what are the relationship? L1, L2, their union is sigma star, their intersection is phi. So now what you can say? Please tell me. So can I say L1 is L2 complement? Yes or no? L1 is L2 complement. They are complement of each other. Agree with me? Okay, I am just taking n equal to 2. Just take n equal to 2. If you take n equal to 2, their union is sigma star. L1 union L2, that is sigma star. Their intersection is phi. Okay, because nothing is common. Every string belongs to exactly one of them. Whatever string you take, that will belong to exactly one of them. Okay, so you can see they are complement of each other. So if you take n equal to 2, if you take n equal to 2, then what languages you will get? Then you will get these languages, L, L complement, L, L complement, and they are both RE. They are both RE, that is given. They are both RE. This is given, right? This is given in the question, because in the question it is given in the big words, recursive enumerable. You can see in this is already given that you have recursive enumerable. Okay, so these are RE. Now you tell me, if both are RE, what will happen? If both are RE, L complement, L, L complement, both are RE, what will happen now? I already told you, complement theorem of RE languages. What will happen? If both are RE, now what will happen? From the complement theorem, just apply complement theorem of RE languages. L, L complement, if both are RE languages, if both are recursive enumerable languages, then they will be decidable or not? Then are decidable. Yes or no? Is this clear? Then they will be decidable. They will be recursive. Yes or no? Is this clear? Please tell me. Let me know. Understood? So now can you get the answer? What will be the answer? So you can see if you take n equal to 2, please understand, if you take n equal to 2, then two languages you will get. In this situation, you will get two languages, L1, L2, and we have seen both will be decidable. And we have seen both will be decidable. Both decidable. So which options are gone? So which options are gone? Each will be undecidable. This is gone. At least one of them will be undecidable. This is gone. Everything will be decidable. Answer is option B. So this question is quite simple, right? Is there anyone here who is thinking that, yeah, this is simple question? Okay, basically you are using a standard theorem. To solve this question, we are using a standard theorem. Okay, there is a standard theorem, remember. I don't know if you don't know or not, but this is a standard theorem. In our Go classes lectures, we have already seen this with proof. So this is actually standard theorem. Okay, you can see this lecture is already available on the Go classes YouTube channel. You can search it. Just search this, Go classes closure property RE. This you search on the Google. I will put the link in the description, don't worry. This lecture link in description I will put. You can check it out. This lecture you can check it out. In this lecture we have basically seen all the closure properties of RE and recursive languages. With proof we have seen. So you can see. Okay, all the closure properties of recursive enumerable and recursive languages, these we have seen in this lecture. Closure properties of RE and REC languages. Complement of RE languages. This theorem, complement of RE languages. Okay, so please watch this lecture for your benefit. Okay, for your benefit, watch this lecture. Very simple lecture. This is a 3-hour lecture, but you will get to learn a lot. Okay, if you watch this lecture, you will learn a lot of things you will learn. Okay, so this is a standard theorem I am telling you. I am just saying that this is a standard theorem that if L, L complement are both RE, are both inside the RE circle, are both recursive enumerable, then they will be decidable. Then they are decidable. Okay, so this is the simple point. Okay, it means that if they are both RE, in the RE circle if you put them, this is your RE circle. In the RE circle if you put L also, L complement also, then they definitely will belong to the REC circle. then they will definitely belong to the REC circle. So this is what this theorem says. Okay, so you can easily solve this question. Just take n equal to 2. You will get L1, L2, where they are complement of each other. Okay, they are complement of each other. L1 is complement of L2. If both are RE, then they both will be decidable. Answer will be option B. Okay. Now, is there anyone here who want the general solution? Who is curious for the general solution? Like how to prove for any random n? This question is taken from Stanford University. Okay. This question I have taken from Stanford. Now, I will share the source. Shreyas is saying, sir, can we have the source of this question? I will share it. Don't worry. Okay. You can just comment under this question. Okay. Just comment. I will share in the reply of your comment. Okay. Now, anyway, so tell me, how will you prove? Now let me give you the complete solution. Okay, let's see the complete analysis. The correct proof. Okay, let me tell you the complete proof. Let me tell you. Okay, so let me tell you the complete proof. Actually, see this question. The question is saying that there are n languages. Okay, the question is saying that there are n RE languages. First of all, what RE language means? When I say you have RE language, what that means? Just tell me. When I say you have RE language, what that actually means? Please tell me. If you have RE language L, what that means? If you have RE language L, there exists a Turing machine, right? There exists a Turing machine M. Okay. So if you have a RE language, then what will happen? This type of Turing machine will be there. There will be a Turing machine. What is the behavior of this Turing machine? If you have a RE language, what will be the behavior of this Turing machine? This Turing machine will have this type of behavior that if the input is from L, if you give input from L, if W belongs to L, then this Turing machine will halt and accept. This Turing machine will halt and yes. Okay. Now, this same Turing machine, if you give input, which is not in L, if you give input which is not in L, now what this Turing machine can do? This Turing machine, either it can halt and no, either it will say halt and no, or it can never halt, or it will never halt. We can also say loop, or it will never halt. That is called loop. Okay, yes or no? So this is the behavior of Turing machine. Correct. Very simple. Remember, if I say L is RE language, then there exists a Turing machine. Okay, and this is the behavior of Turing machine, that to this Turing machine, if you give W belonging to L, so basically here you can see W is a member. If you give W is member of Turing machine, right? W is member. Okay, so basically because W belongs to L, so if you give this W, then Turing machine will definitely halt and yes. In this situation, it will definitely halt and say yes. But remember, if you give a string which does not belong to L, then this Turing machine, either it will never halt or it will halt and say no. Okay, so this is the point. Now the question is saying that there are n RE languages. Okay, all of them are RE languages. L1 is there, L2 is there, and so on Ln. So how many RE languages you have, finite or infinite? How many RE languages you have, finite or infinite? Tell me. First of all, you tell me how many are there, finite or infinite? Of course, you have n. So that of course will be a finite. This n belongs to natural number, right? N will belong to a natural number. So remember, this is a finite collection only. This is only a finite collection of RE languages. Okay, this is not infinite. We are not saying ... No, you have n RE languages. You have n RE languages. For example, you have 10 RE languages, 20 RE languages, 1000 RE languages. Okay, 1 crore RE languages, 1 trillion RE languages. But the point is, this is a finite collection of RE languages. Okay, so these RE languages you have. Because these are RE languages, so what will happen? The name itself is telling you. There is a Turing machine for this. There is Turing machine for this also. There is Turing machine for this also. Yes or no? There is Turing machine for this also. You agree with me? So there are Turing machines. Now you already know that they have nothing common. You already know this is given to you, that their union, if you take their union, that will be sigma star. If you take their union, that will be sigma star. and if you take their intersection Li intersection Lj, that will be phi, nothing common. So these are the things that are given to you so far. Now what I will do, now I can create decider for L1. What I can do, now we will prove that. Okay, now what we will do, now we will create decider. Now we can create, very simple, basically now we can easily create, decider for L1. Okay, what I can do, I can create decider for L1. Decider means what? What is decider? Decider is the halting Turing machine. What is decider? Decider is a halting Turing machine which will always halt. This is halting Turing machine, or you can say, some people they call it total Turing machine. So what is decider? If you have a decider M, okay, let's assume there is a decider M. Now remember, this will always halt, yes or no? This decider M, if you have for some language L, then remember, whatever string you give, this will always halt. Whatever, any string you give, whatever string, okay, any string you give, if you give any string, okay, any string you give, then it will always halt. This is the definition of decider, that it will always halt. It is halting Turing machine. Okay, actually what it will do, let me tell you, this decider, this is the decider Turing machine. So if you give member, it will actually halt and yes. It will halt and it will say yes. Okay, but if you give a non-member to this decider, there is a decider here, it will always halt. This decider will always halt. Okay, so if you give a non-member here, now what it will do? It will halt and say no. It will halt, but it will always halt. It is always halting Turing machine. So this is the decider. Now can you create decider for L1? Okay, just create decider for L1. What I will do, just create decider for L1. So the idea is quite simple. Let me just tell you what the idea. The idea is like this. Okay, just let me tell you. The idea is very simple. I will create decider for L1. Okay, if I can do this, then what I can say? If I can do this, just tell me. If I can create a decider for L1, then what I can say? I can say L1 will be decidable. Yes or no? If I can create a decider for L1, then L1 will be decidable. So now, can you create decider for L1? Yes, I can create. What I will do? Notice what I will do. This decider I am creating for L1. Okay, this decider I am creating for L1. So just for simplicity, I am just assuming that, let's assume you have 3. Let's assume for simplicity. Okay, just assume n equal to 4, or maybe whatever you want. Just assume n equal to 4. So means you have 4 RE languages. You can take any L, but you have 4 RE languages: L1, L2, L3, L4. Okay, for simplicity, I am just taking 4 RE languages. You can take 5, 6, any. Okay, you can take any n. The same proof will work for any n. Now what I am going to do, all of them have Turing machine. You already know this has Turing machine. This has Turing machine M1. This has Turing machine M4. There is a Turing machine M4. This has Turing machine M2. And this has Turing machine M3. Because these are RE languages. All of them are recursive enumerable languages. Now what I am doing, I am creating a decider for L. This decider I am creating. In this decider, what I will do? Notice. This is the decider. This is the decider M for L1. Okay, so here what I will do? Here this is what I will do. I will run whatever string you will give me. What I will do? Notice. Okay, here inside I will put this M1. Inside I will put this M2. I will put this M3. Okay, inside this M3 I will put, and M4 I will put. Is this clear? I will put all of them. Now whatever string you will give me, you don't know what is inside. You don't know. But whatever string you will give me, what I will do? This is what I am going to do. If you give me some string W, then I will run this W on all of them. On all of them I will run this W. Is this clear? Now there are 2 possibilities. I am creating for L1, right? If I am creating decider for L1, then there are 2 possibilities. I am creating, this is the decider for L1. What is this? This is the decider. This is the decider for L1. Now there are two possibilities. What are those? If I'm creating decider for L1, then what should happen? If I'm creating decider for L1, then what should happen? Then this should happen. This should happen. What should happen? Following should happen. I can say that the following should happen. What should happen? This should happen that in this M, if I give W belonging to L1, what this should do? If I give W belonging to L1, then this should say halt and yes. Yes or no? This should say halt and yes. And if I give W does not belonging to L1, if I give W does not belonging to L1, then what should happen? Then this should halt and say no. This should happen, right? The following should happen. Now notice what I will do. Very simple. You just give a string. Okay, let me give you this string W belonging to L1. Then what I will do, I will run it here also, here also, here also, here also. Okay. Now because see, this is a Turing machine, and if you are giving a member, what this Turing machine will do? This is a Turing machine, right? This is a Turing machine. 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 So this is Turing machine for L1. If you give a member, what it will do? What this Turing machine will do? This is a Turing machine M1 for L1. So if you give a member, what it will do? Tell me what this Turing machine will do. If you give a member, this M1 is Turing machine for L1. If you give a member, it will halt. It will halt and it will say yes. Correct? Yes or no? Very simple. So this is what I'm telling you. So you can easily see here definitely halt and yes will come. Okay, here halt and yes will come. What will come here? Here halt and yes will come. Now I don't care here. I don't care. Okay, now I don't care. Okay, here also I don't care. I don't care what they will do. Here also I don't care. Okay, yes or no? As long as this halt and yes is coming from M1. If this halt and yes is coming, now what I will do? Now I will give the final result, that is halt and yes. Okay, is this clear? Okay, because of this halt and yes. If this halt and yes is coming, so the final result I will give, that is halt and yes. So these strings are done. W belonging to L1, these are done. What if W does not belong to L1? If this string comes, W does not belong to L1. Now what will happen? If this string comes, W does not belong to L1. Okay. Now these are Turing machines, right? This is a Turing machine, this is a Turing machine, this is a Turing machine, this is a Turing machine. Okay. You tell me here, just tell me this simple point. If L1 does not belong, if W does not belong to L1, it will definitely belong to any of them. Yes or no? Okay, see, these small things you tell me. These 4 RE languages you have, right? You have total 4 RE languages. What are L1 union, L1, L2, L3, L4? Okay. Now, you just tell me one thing. If L1, if W does not belong to L1, then where it will belong? If W does not belong to L1, in the question it is saying that it will belong to exactly one of them. If W does not belong to L1, then W belongs to one of them, at least one of them. Yes or no? Then W belongs to L2 or L3 or L4. Yes or no? In this situation, W will belong to one of them, either L2 or L3 or L3 or L4. Okay. Second point you tell me. So this is the point. Remember, this is the point. Please understand that. Okay. Please understand that if W does not belong to L1, then from the question you can easily see W will definitely belong to at exactly one of them, right? L2 or L3 or L4. The second point, this is your Turing machine, M1 for L1. Okay, if you give a string which does not belong to L1, now tell me what this Turing machine will do. Tell me what this Turing machine will do. If you give a string which does not belong to L1, this is your Turing machine for L1. If you give a string which does not belong to L1, what this Turing machine will do? In this situation, Turing machine, either it can loop or it can halt and no. Yes or no? Agree with me? either it will loop, or it will say halt or no. Okay, so remember, either it will never halt. This Turing machine, either it will never halt, or it will halt and say no. So this is what I'm telling you. So very simple. If W does not belong to L1, then here I don't care. Okay, here I don't care. But one of them will halt and yes. Okay, yes or no? Because if W does not belong to L1, then it definitely belongs to L2 or L3 or L4. Yes or no? If this W does not belong to L1, then this W belongs to either L2 or L3 or L4. I'm running this on everything. This W I'm running here also, the W running here also, here also, here also. Now, one of them will definitely halt and yes. Okay, this will definitely halt and yes. Okay, this will definitely halt and yes. If this halt and yes will come, okay, because remember, W will definitely belong to one of them. So definitely, one of them will say halt and yes. For example, let's assume M3 is saying halt and yes. This machine M3, this Turing machine M3, let's assume this is saying halt and yes. Then what this M1 will get to know? If this M3 is saying halt and yes, then what this M1 will get to know? If this L3, if this is saying halt and yes, then this M1 will, what it will get to know? This M1 is watching it. Okay, this M1 is watching, remember, this M1 is watching it. This is actually watching. This is watching it. Okay, now in this situation, what we will do? In this situation, we will just simply say that this W does not belong to L1. Here we will just simply say halt and no. Okay, because M3 is accepting W, it simply means that W does not belong to L1. W does not belong to L1, right? So you can see, if one of them is saying halt and yes, then what we will do? We will say halt and no. So we have created a decider. This is the whole proof. Did you understand? So we have created a decider, remember. Basically, this machine we have created, whatever W you give, we will definitely halt. Whatever W you will give, we will definitely halt. So this decider we have created for L1. We have created the decider for L1. Because for L1 we have created the decider, so L1 is decidable. Okay, similarly you can create decider for L2. Similarly, decider for L2 you can create. Similarly, decider for L3 you can create. Okay, so remember here, these conditions, all these conditions are given to you. You already know. Okay, all these conditions are given. Like Li intersection Lj, that is phi. This condition is given to you. And the union is a sigma star. All these conditions in this question, they are given to you. And from these conditions, we have proven that all Li will be decidable. Okay, is this clear? All Li will be decidable because we have created decider for L1. We have created decider for L1. Similarly, you can create decider for L2, L3, L4. Okay, similarly, decider for L2, L3, L4 can be created. So all are decidable. So all Li decidable. This is the complete proof. Okay. Did you find this interesting, this question? Did you find this previous question interesting? Please tell me. Let me know. Actually, you can easily solve it. If you take n equal to 2, okay, then you can easily solve that question, right? Okay, just take n equal to 2. That is a simple solution. This is simple, I can say 1 minute solution. Simple 1 minute solution, right? Okay, in the GATE exam, if this question comes in the GATE exam, you can just simply take n equal to 2 and then simple 1 minute solution is there. But we have also done complete analysis. But I have also told you complete analysis. Okay. So I hope you found this question interesting. So these are all the theory of computation questions that we have in this test. Okay. So shall we move on? Please tell me. Just let me know. Did you understand? So all the TOC questions we have seen from the All India Mock Test 1, all the theory of computation questions we have already seen. Let me know. Did you understand? Please tell me. Please give me feedback so that I know, I get to know. Did you understand everything? Let me know. The complete analysis, did you understand? Also, did you understand this quick solution? This simple 1-minute solution also I have given to you. For this question, just take n equal to 2. You have simple 1-minute solution. But if you want, I have already provided you the complete analysis of this question. Okay. So please share your feedback. Did you understand this solution? Every question, every theory of computation question that we have seen, did you understand? Let me know. Okay, let's move on now. Now we will solve discrete mathematics questions. So let's start. Let's start with this question. This is a very simple question. Combinatorics questions. We need to count how many kings you can put on a chessboard simultaneously. Maximum how many kings you can put on a chessboard. So let's solve this question. Read this question. Chess is a game played on 8x8 grid with a variety of pieces. In chess, no two kings you can place. So you can see no two king pieces can ever occupy two squares that are immediately adjacent to one another horizontally, vertically, or diagonally. Okay. So basically, two kings you cannot put like this, you cannot put like this. So you can easily see no two kings can be placed in consecutive, or I can say adjacent squares which are adjacent to each other horizontally, vertically, or diagonally. For example, the following is illegal. If you do like this, this is illegal. If you do like this, this is illegal. If you do like this, king here, this is also illegal. So all these three, these are illegal. Okay, these are illegal placements. These are illegal placements. The question is asking maximum how many kings you can put on the chessboard. Maximum how many kings we can put on the chessboard legally. So, how to solve this question? Let's solve it. Very simple. On the chessboard, remember, if you have this chessboard, okay, so for example like this, if you have this chessboard, then in this chessboard, if I put a king here, just tell me, if I put a king here, then you can notice that here I cannot put a king, here I cannot put king, here I cannot put, here I cannot put, 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 right? Yes or no? Okay. But if you have a corner piece, for example, if you have a corner, let's assume there is a corner piece. So let's assume this type of, in this corner, if I am putting king, now where I cannot put, in this corner, if I am putting king, then how many positions are gone? Just tell me. In this corner, if I put king, then how many positions are gone? You can see this position is gone, this position gone, this position gone. Yes or no? In this corner, if I put a king, then these three positions are gone. But remember, in the middle, if I put king, then these many positions are gone. So if you want if you want to put maximum number of kings, then definitely you will start with the corner position. Agree with me? Yes or no? See, very simple. If you start with the corner position, then if I put this king in the corner position, then three positions are gone. But if I start from the middle, if I put the king in the middle, then these many positions are gone. In these many positions, I cannot put a king. Okay, so remember, if I want to put maximum number of kings, what I want to do? I want to put maximum number of kings. Then what is the starting point? Just tell me. If I want to put maximum number of kings, will I start from the middle position or will I start from the corner position? Just tell me. If I want maximum number of kings on the chessboard, on this chessboard, if I want to put maximum number of kings, then I will start from where? Will I start from the middle or will I start from the corner? Yes, I will start from the corner, right? Yes or no? Because if I put this king in the middle, then these many positions are gone. In these many positions, I cannot put a king. Okay, so I will start from here. So this will become my starting point, right? This corner place. This corner will become my starting point. This corner becomes my starting point. Okay. Now what will happen? Now this question has become very simple. Now this is a very simple question. What you can do, basically, on this chessboard, this is a chessboard. Okay, like this you have the chessboard. So just start with the corner position. Here you put a king. Now where you can put a king? Okay, so basically 1 2 3 4. I will give you the general solution also, don't worry. 5 6 7. I will give you the general solution. 1 2 3 4 5 6, and you can put so like this. Anyway, so this is the 8 by 8 chessboard, right? Okay, so here you can see what I can do. I will start with the corner position. I will start from this corner position. Now these positions are gone. This is gone, this is gone, this is gone. Now what I can do? Now the next king I can put here. Now the next king I can put here. Now these positions are gone. The next king I can put here. These positions gone. Next king I can put here. These positions are gone. Okay, the next king, remember, so these two rows are gone. In these two rows, how many? Okay, these two rows are gone. In these two rows, 4 kings I have put. Now similarly, the next king you can put here. Then these are gone. Next king here. Then these are gone. Next king here. These are gone. So basically like that. So finally total how many kings you can put? In these two rows, I can put 4 kings. In these two rows, I can put 4 kings. Here I can put 4 kings. Okay, here I can put 4 kings. So finally total maximum I can put 16 kings. Yes or no? So the answer for this question, that will be 16. Okay, but what is the general solution? The general solution will be what? Let me tell you. Let me tell you the general solution. If you have n by n chessboard, let's assume. If you have n by n grid. Okay, so on a n by n grid, what you will do? On this grid, what you will do? On this grid, this is what you are going to do. Notice. Just very simple point. One thing you guarantee, you tell me, whatever position you take, okay, in this chessboard, whatever position you take, at least how many positions will be gone because of a king? Whatever position I choose for a king, I choose for a king, whatever, remember, whatever position I choose for a king, then tell me how many positions wasted? How many positions wasted? How many positions wasted? How many minimum how many positions wasted? You tell me. Minimum how many positions are wasted? Anyone want to tell me? Minimum how many positions wasted? You can see minimum 3 positions will be wasted, right? Yes or no? Minimum this will happen. If you want to waste minimum number of positions, then this will happen, that you put on the corner. You put on the corner. Here you put. Okay, what you do? You put here. Yes or no? You put here. Very simple. So you can see this 2 by 2 grid. I can say this is 2 by 2 grid. It can take only one king. Yes or no? So the minimum how many positions will be wasted? That will happen in this type of situation. In this type of situation, that will happen. You have a king here. This is gone. This is gone. This is gone. Okay. So this is what I'm telling you. I'm just simply telling you that basically to put maximum number of kings, what you can do? You want to put maximum number of kings. Okay. So if you want to put maximum number of kings, what you can do? Basically, start from the corner. Start from corner. Start from corner place. Okay. Start from corner place basically. Okay. And basically in every 2 by 2 square, just put one king. Okay, like this. Just put one king like this. So basically what you do, start from the corner place, start from a corner place and put one king in every 2 by 2 square. Okay, is this clear? In every 2 by 2 square, one king you can put. Very simple. Is this clear? So very simple. Remember, you will start like this. Okay, whatever you have, you can have anything. Okay, you can have anything you can have. Okay, any big you can have. You start from here. Now these positions are gone. These positions are gone. So you can see in this 2 by 2, you can put one king. Okay, so basically it's like this. Every 2 by 2 square, okay, gets one king. Gets one king. So your final answer will be what? Your final answer. So just find number of 2 by 2 squares. How many are there? Number of 2 by 2 squares. Just tell me. How many 2 by 2 squares are there? That will be n by n divided by 2 by 2. Okay. So you can see these many 2 by 2 squares will be there. And this is your maximum number of kings we can put. This is the maximum number of kings we can put. We can put. Is this understood? Please tell me. Let me know. Is this clear? Please tell me. So very simple. Remember, this is the general solution. If you have an n by n board, then these are the maximum number of kings you can put on a n by n board. So for this question, the answer is going to be 16. And the general solution, what is that? Let me write here. The general solution. The general solution is n by n divided by 2 by 2. This is the general solution. Okay. Let's move on. In the same question, if you have rook, instead of king, if you have rook, now what will happen? Maximum how many rooks you can put? Anyone want to tell me? On 8 by 8 grid, maximum how many rooks you can put? Hathi. In Hindi, maximum how many rooks we can put? Tell me. Rooks. We can put. Let me know. Rook means hathi, elephant. Elephant. So tell me, anyone? Maximum how many rooks you can put? Tell me about it. How many maximum rooks you can put? Actually, rook is like this. See, rook is like this, that it will attack anyone who is in its column or in its row. See, for example, if this is the row, if I put a rook here, then these positions are gone. All these positions are gone. All these positions are gone. Also, this column is also gone. Also, this column is also gone. Okay, all these positions gone. Also, this column is also gone. Okay, so once I put this rook here, this row gone, this column gone. So maximum how many I can put? Very simple. If you have a 8 by 8 board, okay, if you have a 8 by 8 board, then maximum how many I can put? Very simple. I can put one rook here. Now this is gone and this is gone. I can put the next here. Now this is gone, this is gone. I can put the next here. Now this is gone, this is gone. So basically, diagonally I can put total 8. Yes or no? Is this clear? So maximum how many I can put? So remember, max number of rooks. Max number of rooks on n by n grid. If you have an n by n grid, then maximum how many rooks I can put? That will be n. Just put diagonally. Put diagonally. Okay, just put them on the diagonal. Is this understood? Please tell me. Very simple. Just put them diagonally. Okay. So maximum you can put n rooks you can put. Very simple. Okay, let's move on now. Let's solve this question. This is another question based on function from the discrete mathematics. Let's solve it. A function is given to you. F is a function from A to B. A is the domain, B is the codomain. This is a function from arbitrary set A to arbitrary set B. Below is a series of statements in first order logic about this function. Which statement is always true regardless of what f you take? Which statement will always be true? F is already a function, right? The question is saying f is already a function. So what that means? If f is a function from A to B, this is A, this is B. If f is a function from A to B, that means every element of A has exactly one image. Okay, if I take this element, there will be image. This A2, there will be image. This A3, there will be image, right? Okay, so this is the definition of function. Okay, this is the definition of function. So very simple point. In the function, what happens? Every element of the domain has exactly one image. Yes or no? Very simple. In the codomain. So very simple. Every element of the domain has exactly one image in the codomain. So if this function you already have, the question is saying you already have a function. A function is already given to you. Now, which statement will always be true? Whatever function you take. You can take whatever function you want. Which statement will always be true? What about the statement number A? The statement number A. Can I say for all A belonging to A, there is a element in B such that fa equal to B? Please tell me. Can I say if this function you have, is this statement will be true? Let's see the first option. First option means for every element in domain, there is some element in codomain. For every element, remember, for every element of domain, whatever element you take in the domain, there is some element in the codomain. There is at least one element in the codomain such that f of A is equal to B. Yes, this is true, right? This will be true for every function. This will be true for every f. Whatever f you take, this will be true. Whatever function you take, this will be true. For every element, there will be at least one image. Yes or no? For every element, you can take whatever element you want. You can find there exists a image. Okay, yes or no? So this statement, this is always true. What about the statement number 2? For every element in the codomain, there is a element in the domain such that fa equal to B. This will happen only for which functions? This will happen only for surjective functions. Yes or no? This will only happen for a surjective function, right? This statement will only happen for surjective function. Because what is the second statement? The second option. This is saying for all element in B, there exists an element in A such that fa equal to B. But your function is from A to B. Okay, your function is from A to B. This is your function. So you can see that, this statement is actually not always true. This statement is not always true. Not true for all functions. Yes or no? This is not true for all function, for every function. This is not true for all functions. This is actually true only for surjective function. This is the definition of surjective function, right? Yes or no? Okay, this is the definition of surjective function, if you remember. This is a definition of surjective function. Definition of onto function. Okay, so you can see, for example, you can easily see if you have A, B, and you have 1, 2, 3. Now, you can just consider this example. In this example, you can notice this statement is actually false. This option 2, option B, that is actually false for this function. For this function, you can notice this option B is false because look at this, there is no pre-image. Okay, for all element in this codomain, you can see this element is in the B, but there is no pre-image. So you can see this is not correct. What about the next one? For all elements A1 and A2 in A, if they are same, their image will be same. If they are same, their image will be same. Yes, of course. Yes, of course. Yes or no? Because very easily you can see, if you take same elements, your A1, A2, both are same. Both are same. Means basically they are like A. Okay, it's like A. It's like A. So there will be, their image also will be same. Yes or no? Their image also will be same. So if you have same elements, then their image also will be same. So this statement is true for every function. What about the last option? Now the question is saying that for every A1, A2 in A, if their image is same, then they will be same. If their image is same, then they will be same. This is not correct. If their image is same, they will be same. This is not correct. Actually, this will happen only for injective function. This will happen only for injective functions, right? This is the definition of injective functions, right? So option D, that is the definition of injective function. In the injective function, this happens that if two elements have same image, then they will be same element. Okay, so you can see this option D, this will happen only for the injective function. But the question is asking which statement is always true for every function. So answer will be A, C. For this question, answer will be A, C. Is this clear? Amit is saying, sir, first one is not true for partial function. Is the question talking about partial function? Is the question talking about partial function? Function is function. Okay, remember, function is function. Function is function. Function automatically means total function. Function automatically means total function. Actually, we don't use this word, this total function. This is the word. Function is function. Is this clear? The question is not talking about partial function. If you are thinking like this, are you thinking like this, that function has two types? One is partial, another is total. Are you thinking like this? Are you thinking like this, that function is of two types? One is partial, another is total? No, this is nonsense. Okay, function itself is total function. Remember. Okay, is this clear? This is optional. This total word is optional. Partial function is a different thing, but this is basically optional. Optional word. This word is optional. Okay, so partial function is there. For example, partial function is like this. If you have a, b, c, then if you have 1, 2, then you can see this is a partial function, right? Okay, this will be a partial function. This function, you can note, this is a partial function. But here this word is mandatory. Okay, please understand, this word is mandatory. This partial word is mandatory here. This is a mandatory word. This word is mandatory, okay? So this partial word is mandatory. Understood? So partial function is like this. In the partial function, you can see it is not necessary that every element has an image. Basically, it's like this. Partial function is like this. The definition of partial function. Partial function definition. What is that? That every element of domain has at most one preimage. Every element of domain has at most one image. Has at most one image. Okay? And what is the definition of function? And what is the function definition? What is the definition of function? Every element of domain has exactly one image. Exactly one image. Is this understood? Amit, is your doubt clear? See, if you are thinking function has two types, one is partial function, another is total function, this is nonsense. This is nonsense. Function means total function. Okay. Function automatically means total function. This total word is optional. Okay, this word is optional. But remember, in the partial function, this partial word is mandatory. This partial word is mandatory word. Okay, so you can see partial function is like this. For example, this is a partial function. This is a partial function. But here this partial word is mandatory. You cannot skip this. Okay, so very simple. Okay, let's move on now. So for this question, answer will be, we have already seen, answer will be a comma c. Okay, let's move on. Let's solve this question. You can see another question from discrete mathematics. So let's solve it. This is another very simple question. A comma b, these are arbitrary set. A is a set, b is a set. Now, this function is given to you. This partial order is given to you. This is a partial order relation on b over b. Suppose we pick a function. Okay, remember, we are picking a function a to b. Now the question is saying we can define a relation over a as this relation we are defining over a for any x comma y in a. The question is saying that for any x comma y in a, they will be related. X is related to y if and only if fx is related to fy under this partial order. Okay, so the question is asking which statement are true. Some options are given to you, that this is symmetric, this relation is symmetric, reflexive, anti-symmetric, transitive. Okay, so let's solve this. First of all, understand this question, what this question is saying. First of all, a comma b are two set. Okay, see, there are two things here. There is a set b, and on this set b we have already defined this relation. Okay, so on set b, remember, on set b we have already defined this relation, this partial order relation we have defined. Okay, this partial order relation we have defined, partial order relation. Okay, this is the partial order relation that we have defined. Is this clear? Very simple. Okay, so you can see, let's call it RB. Okay, for simplicity, let me call it RB. Okay, for simplicity, For simplicity, let me call it RB. That this is the relation we are defining. So remember, this relation you are defining on B. And this is a partial order relation. What that means? This is a partial order relation. Means what that means? It means that it will be reflexive, it will be antisymmetric, it will be transitive. Okay? Yes or no? This RB. We are talking about RB. This partial order relation, this will be reflexive, antisymmetric, transitive. Now what this question is saying? This question is saying that take a mapping from A to B. Okay, this is set A, this is set B. Take a mapping. Take some mapping from A to B. This function you take. The question is saying pick a function. Okay, pick any function. So here remember, pick any function. Pick any function from A to B. You can take any function. So you are picking a function from A to B. Now the question is saying like this, that now we are defining a relation on this A. Okay, on these elements. Like if you take A1 here, let's assume this is the image is B1. Okay, let's assume you have A2 here and the image is B2. Now the question is saying that, now we are defining this relation. We are defining this relation less than equal to A. Okay, less than equal to A. Basically this relation we are defining on set A. And we are defining like this. So when can I say A will be related to A1 will be related to A2? When can I say A1 will be related to A2? This A1, when can I say it will be related to A2? It will be related to if and only if B1 is related to B2. B1 is related to B2 under RB. Yes or no? Is this clear? Please tell me, did you understand? Let me make you understand. See, okay, let's assume that I am giving you a function here. Okay, let's assume you have A1 here, A2 here, A3 here. And you have B1 here, B2 here, B3, B4. Okay. So let me assume that B1 is related to B2. Okay, basically let me assume like this, that B1 is related to B2, B2 is related to B3, and B3 is related to B4. Okay, let's assume. So you can see. Now in this situation, let's assume these are the images. Okay, because you are taking a function, you are picking a function. So you can take any function. In this situation, you can take this function, right? In this function, you tell me who will be related to whom. Who will be related to whom? This is already given to you. Okay, what I'm telling you, this is already given to you. This is already given that B1 is related to B2 under this relation less than equal to B. B2 is related to B3 under this relation. B3 is related to B4 under this relation. Okay, now you tell me, in this A, who will be related to whom? Okay, see, this is already given to you, right? Now what you are doing, you are taking a function. This function I have taken. Now in this function, after taking this function, you are defining a relation on A. You are defining this relation. What you are doing, you are saying that you are defining a relation. You are defining this relation on A. Okay, let me just make some changes here. So that you will understand what is happening here. Let me make some changes. Let me assume that A2 is here. A2 is mapping to B3. A2 is mapping to B3. And let's assume A3 is mapping to B2. Okay, now tell me, you are defining a relation. Okay, now you tell me who will be related to whom? A2, A3. Who will be related to whom? Tell me which statement is correct. Can I say A2 will be related to A3? Or can I say A3 will be related to A2? You are defining a relation on A. Who will be related to whom? Tell me. Can I say A2 will be related to A3 or A3 will be related to A2? You can see that A3 will be related to A2, right? Why? What is the reason? The reason is very simple. See, very simple. This is A2, this is A3. A2 is mapping to B3 and A3 is mapping to B2. Now you can notice that A3 will be related to A2. A3 will be related to A2. Why? What is the reason? Because f of A3. Because what is f of A3? F of A3 is B2. Because f of A3 is related to, under this relation less than equal to b, is related to f of a2, right? Yes or no? Is this clear? Please tell me. Let me know. So this is the question. Did you understand the question? Please tell me. Once you understand the question, now you can solve whether this, now you find out what will happen. Reflexive property, will it be satisfied? Will it be satisfied? The reflexive property, will it be satisfied? Means if I take some element here, can I say a will be related to a? Just tell me, can I say a will be related to a? Is this statement correct that a will be related to a? Will this statement be correct that a will be related to a under less than equal to a? This is the relation you are defining on a, less than equal to a. Tell me, can I say a will be related to itself? Yes, it will happen because the image is, let's assume the image is b. Okay, so you can see f a equal to b. Okay, this will happen. This is true. This is true because, why? Because you can notice fa is related to fa. Who told you? How do you know? How do you know fa is related to fa? Tell me, how do you know fa is related to fa? How do you know? Let me know. Please tell me, how do you know that fa is related to fa? Means this b is related to b. This b is related to b. How do you know this b is related to b? Because already it is given this is partial order. Already it is given this is partial order, right? This is already given to be partial order. So this is already reflexive. This relation is already reflexive. This relation is already reflexive. Is this clear? Please tell me. Because in the question, this relation is already given to you as reflexive. Look at this. This is a partial order. So this relation less than equal to b, this relation on set b is partial order. Is partial order. So this is reflexive. So very simple. So that is the reason you can say that this will also happen. This will be related to this. A will be related to A. So reflexive property is satisfied, right? Okay, yes or no? Reflexive property is satisfied. So this relation will be reflexive. That is correct. That is correct. What about the second? Symmetric. What about symmetric? Will it be symmetric? This less than equal to A, will it be symmetric? Can you give a counter example for symmetric? Will it be symmetric? No, this need not be symmetric. For example, let's assume you have A1 here, A2 here, B1 here, B2 here, B3 here, and A3 here. Let's assume you have this type of situation. Now what you can notice that, let's assume that this is happening. Okay, here I am telling you that B1, okay, or maybe you can just take two elements. Just take two elements, that's enough. Okay, just take these elements. This function you take. Now you can easily see that, let's assume that B1 is related to B2 under this is, let's assume. Now in this situation, who will be related to whom? Now who will be related to whom? Remember one thing, this is actually antisymmetric, right? This is already given to you. This relation is antisymmetric. This relation is antisymmetric. Because this relation is antisymmetric, so B2 cannot be related to B1. Yes or no? If B1 is related to B2, so B2 cannot be related to B1. This relation is actually antisymmetric. So B2 cannot be related to B1. Agree? B2 cannot be related to B1. Okay, so now you tell me, what about these two? Will it happen or will it happen? Will both happen? Will both happen? Please tell me. Will both of them happen? Yes, this will happen, but this will not happen, right? Yes or no? So you can see symmetric is gone. So this symmetric is gone. Understood? Please tell me. Did you understand this? Just take this function, because you can take any function. Just take this function f. In this function you can notice b1 is related to b2 under this relation less than equal to b. This less than equal to b, this relation is actually antisymmetric. So if b1 is related to b2, then b2 cannot be related to b1, because this is already given to you that this less than equal to b, this is antisymmetric. So now you can see that a1 will be related to a2, but a2 is not related to a1. So I can say this less than equal to a. This is not symmetric. So symmetric is gone. What about antisymmetric? This less than equal to a, can I say this will be antisymmetric? This less than equal to a, can I say this will be antisymmetric? For example, take this function. Okay, I am giving you a function. You take b1, b2. Let's assume b1 is related to b2 under less than equal to b. Okay, let's assume this is happening. Now consider this a1, a2. Now consider this. Let's assume a1 is also mapping to this, b1 is also mapping to this. Is this possible? Is this type of function you can take? Please tell me, can you take this type of function? Let me know. Can you take this type of function? Please tell me. Can you take this type of function? Let me know. This type of function can you take? That a1 is also mapping to b1 and a2 is also mapping to b1. This type of function can you take? Can you take this type of function? Yes, because you can take any function. Because you can take any function, right? Okay, this type of function you can take because you can take any function. You have any function f from a to b. You can take any function. So you can take basically this type of function you can take. Now you tell me, if you can take this function, now something interesting will happen. Can I say a1 will be related to a2? Can I say a2 will be related to a1? Yes, both will happen. This will also happen. This will also happen. This will also happen. Yes or no? a1 related to a2, a2 related to a1. So these will happen. So I can say this may not be antisymmetric. Yes or no? This may or may not be antisymmetric. This may or may not be antisymmetric. Is this clear? Did you understand? Please tell me. Let me know, did you understand? Because if both are mapping to b1, it's like this. If both are mapping to b1, this a1 also, a2 also. If both are mapping to the same element, if they are mapping to the same element, now you can easily see that a1 is also related to a2. a1 is also related to a2 because you can see, because b related to b, because b related to b, and similarly a2 is also related to a1. Similarly a2 is also related to a1 because b is related to b. Okay, so you can see antisymmetric is gone. Yeah, yes or no? This is not antisymmetric. a1 related to a2, a2 related to a1. This is not antisymmetric. This, so you can see this may or may not be antisymmetric, right? So this option C is also gone. Can you tell me in which situation you will have antisymmetric? Can you tell me when? Just tell me when this will definitely be antisymmetric. When this relation will definitely be antisymmetric. Please tell me in which situation this will definitely be antisymmetric. Tell me in which situation this will definitely be antisymmetric. This relation will definitely be antisymmetric. In which situation? When it will happen that this will definitely be antisymmetric? When f is injective, right? Yes or no? When f is 1 to 1, or I can say injective. If f is injective, then it will definitely be antisymmetric. Okay, means if f is injective, a1, a2, a3, if f is injective, then you will definitely, you cannot have these, like for example, if you have injective function, okay, let's assume you have this type of function. So if you have injective function, okay, if you take this function f, now this less than equal to a will definitely be antisymmetric. Will definitely be antisymmetric. Right? Yes or no? Okay, when it is injective, when it is 1 to 1, then this will definitely be injective. Okay, very simple. You can just check it out. Anyway, what about transitive? What about transitive? This will be transitive. How can you prove it? This will be transitive. See, very simple. Just tell me one thing. Okay, let's check the transitivity. Let's check option, this transitivity. Transitivity. Let's check for transitivity. You just tell me one thing. this is your A. Let's assume you have A1, A2, A3 and so on. Okay, now you just tell me this is the set A and this is the set B, right? B1, B2 and so on. Okay, now you tell me if for transitivity you tell me if A1 is related to A2, A2 is related to A3, can you guarantee A1 will be related to A3? Tell me, can you guarantee? Then can you guarantee if A1 related to A2, okay, under this relation, okay, if A2 related to A3 under this relation, then can we guarantee, then can we guarantee, then can we guarantee that A1 will be related to A3? Please tell me, can you guarantee that A1 will be related to A3? Is there a guarantee? Yes, there is a guarantee. Just apply the definition. Just apply the definition. If this is happening, what this means? A1 related to A2. A1 is related to A2. What this means? A1 related to A2. What this means? This means f of A1 is related to f of A2. Yes or no? F of A1 related to f of A2. Okay, and what this means? What this means? This means f of A2 is related to f of A3. Okay, so you can see f of A1 related to f of A2, f of A2 related to f of A3. So you can see f of A1 related to f of A3 because this is transitive. Because this is transitive. This is already given to you. This is already given in the question. Okay, this is a given in the question. So finally I can say that A1 will be related to A3. Okay, A1 will be related to A3. So transitive property satisfied. Okay, so I can say this less than equal to A is also transitive. Is also transitive. So I hope you understood this question. This similar type of question has come in the GATE 2023 also. Have you seen? In the GATE 2023 also, similar type of question has come. Similar type of question has already come. This question is also taken from Stanford. This question, this beautiful question is similar. Let me tell you, a very similar type of question has come in GATE 2023, in GATE Computer Science 2023. This question I have taken from Stanford. So you can see this is true. So the question is asking which statement is true. The answer will be A, D. In the same question, if injective function is given, then what will be correct answer? In the same question, okay, in the same question you tell me if injective function is given. If in previous question, if f is injective, if f is an injective function, then which options will be correct? If f is injective, then answer will be ACD. Then answer will be ACD. Okay, then in this situation answer will be A also, C also, D also. Okay, so I think this is enough for today. Okay, so in this session, whatever we have seen, all the questions that we have seen, the complete analysis that we have seen, please tell me, did you understand? You tell me two things. Did you understand? Also, did you learn something new? Please tell me, did you learn some new things in this session? Some interesting, some new things did you learn? Please tell me, let me know. Okay, so please comment. Okay, so tomorrow we will continue, don't worry. Okay, so tomorrow we will continue this discussion of AIMT 1. So far we have discussed all the questions from theory of computation and some questions from discrete mathematics we have seen. The remaining questions we will do tomorrow. So tomorrow we will do DBMS, digital logic, also the computer organization questions, okay, and the remaining discrete mathematics questions, okay. So the remaining questions we will do tomorrow. So please tell me, please give me your feedback, okay, after this session is over. So please put a comment, okay. So please let me know, did you learn something new? Which was your favorite question? And did you understand the complete this solution. Basically in this session, every question that we have seen, the solution of every question, did you understand? Every point that I told you, did you understand? Let me know. Okay, so thank you everyone, see you tomorrow. So please put a comment. Okay, please like and comment if you learned something new in this session. If this session benefited you in some way, then please put a comment, share your feedback. It will motivate us. Okay, your comments we read. I and Sachin, we read all your comments. I personally read all the comments on the Go Classes YouTube channel. So your comments, they motivate us. Okay, so please put a comment under the video, put your feedback, and please like and share with all the aspirants. Okay, so thank you everyone. See you tomorrow. Tomorrow we will continue. We will see the remaining questions of AIMT 1. We will see computer organization, DBMS, digital logic, and the remaining questions of discrete mathematics.